Is it good now? Okay. Okay, yeah. Yeah, we still have a minute, so let's start on time. All good? Okay, thanks. Cool. Okay, I think we can get started. Okay, today we're going to cover a lot of things, a lot of exciting topics again, but I'm going to finish instruction prefetching first, which I promised in the last lecture, but we couldn't get a chance to cover. Let's see how much time we spend on it, hopefully not too much. And then we're going to switch into more, let's say, multiprocessor type of topics of this course. We're going to start with heterogeneity and bottleneck acceleration, which is really important, I think. If I was giving this lecture, let's say, actually, I was giving this lecture 15 years ago or so, and there were no heterogeneous processors at the time. Today, we have heterogeneity is a very common thing, right? When you look at the processors, there's always performance cores and efficiency cores, whatever they call them, strong cores, weak cores, large cores, small cores, as we used to call them. So this is an area that has clearly had impact, but I'll give you a history of it also a little bit. But before that, let's wrap up prefetching, as I said. And for prefetching, we've covered a lot. And these are some slides that I added this year. We normally don't talk about instruction prefetching, but I think it's good to talk about it a little bit also because it's an important area. Maybe it has less potential, in my opinion, than data prefetching because data is very wide, right? Data sets are huge. Instruction sets are usually smaller, but that doesn't mean that all instruction sets are smaller, especially with, let's say, code bloat and these languages that make programmers' life easier. There's a lot more instructions to process. And also, I guess in some models, some execution models where you execute short pieces of code and not very long pieces of code, instruction prefetching can be very, very beneficial. But essentially, instruction prefetching, the key idea is very simple. You predict which instructions will be needed by the program and fetch them proactively, as opposed to data. And all of the questions we discussed apply. All of the techniques we discussed apply. The major difference from data prefetching is instructions are really accessed sequentially, whereas data, not always the case. In fact, not usually the case. And this happens because of the von Neumann model, right? There are two key principles of the von Neumann model. If you took DDCA, you would remember those principles. Anybody remembers those principles? Anybody take DDCA? One is a sequential execution, and the other is a stored program computer. You store the program and you execute it sequentially, essentially. Unless, of course, there's a control flow change. When there's a control flow change, there's an explicit redirection of the program counter. In fact, program counter, program counter points to the current instruction that's executing, right? It's called a counter because you sequentially increment it, essentially, normally. And that's why instruction prefetching sequentially works very well. But of course, when there's a control flow change, this is broken. So you need to predict the branches and figure out where the next instruction may be coming from. Because of the sequentiality of the sequential nature of instruction execution, simple streaming or next line prefetching is usually effective. But we will see a little bit more than that. So next sequential instruction prefetcher, we've seen next sequential data, essentially always prefetch next n instructions, in this case, after a demanded instruction. This works well when program executes sequentially without branching. Right? We've seen this for data also. If you're streaming through data, this also works nicely. And this is actually a very old idea. The first incarnation that I know of is really IBM 36091, which is a beautiful processor. It's one of the first out-of-order execution processors. It's not the first, but it's one of the first. And there's a beautiful paper that talks about this. If you're interested, you can read one of these papers. It also implements Thomas Sowell's algorithm. But you can see that there's instruction fetch buffers over here. But those are really, some of those are really used for prefetching. And again, I will not go through this, but at the time, processors used to be less complex, where you could actually specify the flowchart of the sequential instruction supply function like this. And you can read it if you're interested. They actually look at whether the bus bandwidth is available to the next level, and then they decide to do prefetching, etc. But today, it's very difficult to specify things like as easily like this. It's good to think about that. This is from 1967. Okay, so people have been doing actually sequential instruction prefetching for a while. These are more recent papers. Again, I will not go through the details a lot, but a lot of ideas that you've discussed apply. So, okay, you don't want to prefetch every n blocks when you're prefetching next sequentially n blocks. Maybe you want to figure out which ones are actually going to be useful. And one way of figuring out which ones are going to be useful is whether the instructions that you have prefetched last time were used before. So basically, you add some metadata into the cache or the prefetch buffer, and you basically keep track of which cache blocks that you prefetched were useful using one prefetch bit for cache line. And if you think, whenever you go through those instructions again, you decide which ones to prefetch and which ones not to prefetch based on past useful. So somewhat similar to throttling that we have used, but it's a little bit different also in nature. So this aims to be more accurate than a naive prefetcher, next n-line prefetcher. I don't know why they did just 4 lines. It's a little bit hard-coded. I don't like that kind of hard coding in general in papers, but that's how it is. But of course, the downside is now it's more complicated. You need metadata to identify which blocks are used, right? But that was true for feedback-directed prefetching, right? As we have discussed, right? That worked. And then people also applied other ideas like correlation prefetching to instruction prefetching. This is an interesting paper that talks about, again, building on the next n-line prefetcher. They basically say next n-line prefetcher might be late because, again, you're running ahead, and as a result, by the time the prefetcher starts the next n-line fetches, the instruction engine is already there, almost, right? You don't essentially, you're not timely enough. So in this paper, what they do is they essentially do correlation prefetching. They identify an iCache misaddress. Basically, they correlate. Whenever they find an iCache misaddress, they correlate it to an early enough iCache access that hopefully is going to cover the latency of the prefetch. That's the idea. And for that, they have some mechanism to predict or calculate how long an iCache miss will take, etc. You can take a look at it if you're interested. But the basic idea is correlating a cache miss with a much earlier access so that whenever you see that access again, you start that cache miss next time. So it's very similar to Markov prefetching in a sense, right? We've discussed this idea, except it's specialized and applied for instruction prefetching. And you can read the paper. I'm going through these quickly. You could actually imagine other ideas. But I'm going to talk about one thing that is actually employed, that has been employed in many processors, which is fetch-directed instruction prefetching. At the instruction level, whenever you're in the front end of the machine, you have actually a lot of information about what you can do. And fetch-directed instruction prefetching essentially executes or exploits that information. So the key observation is that whenever you execute instructions, you essentially have a series of consecutive cache block accesses you have because it's all sequential cache blocks. But then there's a gap sometimes, meaning you jump somewhere else in the program due to control flow. If you can somehow identify those gaps and predict those gaps, you can actually prefetch things early. So we already do that actually with branch prediction, right? Branch prediction already does that. So the idea over here is to run the engine, run the front end of the machine faster, and prefetch the instruction to a queue. While the back end of the machine is stalled, you can keep prefetching instructions to this queue, and you can keep predicting. So the idea is actually really decoupling the front end of the machine and the back end of the machine. Back end of the machine can be stalled for many reasons, as we have discussed, memory, for example. But front end of the machine can keep going almost forever. The back end of the machine can be actually stalled for 1 million cycles. but the front end of the machine can be fetching instructions, predicting branches, and execute, essentially going through the control flow of the program and feeding instructions into a queue, which is the fetch target queue, for example, instruction buffer, as long as it can actually predict instructions and keep fetching. This way, what you can do is, while the backend of the machine is stalled, you're really overlapping the latency of the backend execution with the latency of the instruction cache misses, right, if you're thinking about it. And this way, you can also overlap the latency of the branch predictions. So this is a general idea of decoupled front end. You're really decoupling the front end from the backend with a queue in between. And and by doing so, if you're really bottlenecked by the backend, hopefully you'll not be bottlenecked by the front end, unless you mispredict branches, of course. Whenever you mispredict a branch, these things may not be very useful, right? Okay, so I've already described actually a lot of things that are going to come in the next slides. But if you look at the execution of a program, these are basic blocks, control flow blocks. You can see that there are a bunch of instructions, and there's a branch. There are a bunch of other instructions, there's a branch, and there are a bunch of instructions, there's a branch. So what you're really trying to do is go through this basic blocks. And the instruction stream may look like this. You basically predict this branch taken and this branch also taken. And the idea, as I've kind of said, is you direct the prefetcher by predicting branches among prefetched instructions. This also could be called branch predictor directed instruction prefetching. But as I said, it's a more common philosophy, not just directed at prefetching. The philosophy is really decoupling the backend of the machine from the front end of the machine. That's really the principle. And that actually provides a lot of other benefits, like running the front end faster while the backend is stalled, or running the front end while the backend is stalled. And that way you can actually prefetch instructions and predict branches. Does that make sense? Okay, so it's a very simple idea if you think about it, but I'll show you some interesting results from a recent paper from ARM, which shows that this idea, if you actually implement it nicely, maybe you don't need other prefetchers for instructions. That's what they suggest. If Rahul was here, we would also ask his opinion. He's not here. Okay, so basically, I think I've already said this. From the current instruction, you start prefetching sequentially. If you encounter a branch instruction, predict the target address of the branch and keep prefetching sequentially until you encounter another instruction. This way, fetch engine can run far ahead of where in the program the execution units are currently executing. And as I said, this is decoupling the fetch engine from the rest of the pipeline. And what do you do with the instructions that you prefetch? In this case, you put them into a fetch target queue. And this target queue is really a FIFO queue. It's really the predicted instruction stream. And you can also decode them, actually. You could actually put the decode stage into the fetch part as well, as long as you need to decide where the decoupling happens between the back end and the front end, of course. And the next stage, it could be a decode stage, or it could be the rename stage, for example, an out-of-order execution processor, consumes entries from the fetch target queue and processes them. There should be processes them over there. Okay, so this is an example. Probably a picture is worth 1,000 words over here. Here, there's a fetch target queue. This is one example implementation. It's not the only example. I think there may be better implementations, actually. This is from a recent paper that talks about it. Essentially, you have a fetch target queue. It creates a bridge between the instruction address generation unit and the instruction fetch unit. And what you do is this address generation unit keeps on generating instruction addresses using the branch predictor. And essentially puts the instruction addresses over here. And then the prefetch requests are sent to the iCache, and the instructions are essentially buffered over here or over here. Okay, I'll go through this relatively quickly because I've described the ideas essentially. So once you have a misprediction, of course, there's a downside, right? This decoupling doesn't help if your branch predictor is not accurate. If you have a misprediction, you're back to square one. Your fetch target queue is flushed after every instruction that comes after that mispredicted branch is flushed, and you'll need to really start fetching instructions again. So mispredictions are not useful for this case because you're really using the branch predictor. Okay. So this is an old idea. This is one of the papers that described the idea. As you can see from it's from 1999, and it talks. It received a Test of Time award deservedly recently. You can read that paper, and this is implemented in many processors today, especially IEDM processors were one of the first to implement this. These are not the oldest papers, but you can see that they've been implementing in the Z series their mainframe processors for a long time, and they actually have a very sophisticated front end. that they used to describe in some old papers. It's not just IBM, it's also AMD, ARM, Samsung. They've publicly shown that they've implemented this fetch-directed instruction prefetching. Now, the interesting thing is, if you have fetch-directed instruction prefetching, how do you combine it with other prefetchers? So this paper from ARM recently showed that if you actually implement fetch-directed prefetching with a large fetch target queue size and with good enough branch prediction accuracy, maybe other instruction prefetchers are not that good. So this is data from their paper. We have not verified it. Essentially, if you have a small fetch target queue size, and if you disable fetch-directed prefetching, you basically have very big differences between different prefetchers. If you have a very large fetch target queue size, buffering of instructions between the decoupled front end and the back end, and if you enable fetch-directed prefetching, essentially there is not that much difference between different types of prefetchers. These are different types of prefetchers. You don't need to know exactly what they are. So this is interesting, I think. So it's good to think about how do you design the front end, right? So jury is still out over here. Any questions? Yes. Yeah. Yeah. Mm-hmm. Yeah. Yeah. I mean, basically, the same, everything we discussed about memory applies to instructions also, right? If you miss in the instruction cache, then you have to go to memory. It takes a long time. The question is, how often does that happen? I think that's what you're asking. And the answer is, it really depends. If your workload, for example, has a small instruction working set, very high locality, which is usually the case, actually, in general, then this is not a huge problem. But there are some workloads where the instruction working sets are actually quite large. Some commercial workloads, for example, some database workloads where you actually keep doing a lot of different things in the workload, then you're touching a lot of different places in the code. This may not fit in your iCache. And also, it may actually cause a lot of, let's say, accessing different parts of the code. In that case, this is actually a problem. And these papers talk about that problem. And it could be as bad as the data problem, actually. One of the downsides of instructions that's different from data is essentially with data, you can overlap that latency more easily. With instructions, if you have an instruction cache miss, you're not filling the pipeline anymore, right? So it could be more severe. But the occurrence, I think the frequency of occurrence of instruction cache misses are, in general, much lower than data cache misses. That's why we deferred it to this late. And we have not talked about instruction prefetching as much in prior, let's say, years. But I think it's important to talk about it. Okay, any other questions? That was a good question. People are still trying to wake up from the hibernation in the cold. Okay, it's going to get colder. Okay, so there's more recommended material on prefetching. Some things we have not covered are in old lectures, but I'm not going to talk about that. There are a lot of interesting things here, but we don't have time. If there are no questions, I'll very quickly pitch. If you want to do research in these areas or other areas, talk with us. I know some of you are talking with us. Basically, we do research in all aspects of computer architecture, not just memory-centric aspects, processor-centric aspects also. In fact, we're going to talk about some papers, so think about that. And also, I think one of the things that's interesting with prefetching is I cannot really classify prefetching as a completely processor-centric aspect given a memory-centric computing system, right? If you have processing near memory, processing in memory, you may still need to do prefetching, right? Prefetching by itself is not processor-centric because you may need to execute something in memory, but then the data may not be there, right? Basically, it's really targeting the data may not be there problem. And data may not be there for many different reasons, not because you're processor-centric. It's because someone else modified the data, as we will see later on, for example. Right? So I think this is an area that needs to be re-examined a lot in more memory-centric computing systems. And I think that's true, actually, for a lot of the processor-centric concepts. Okay, prefetching may be somewhat processor-centric comparatively, but there are a lot of other processor-centric concepts, like caching, for example, like out-of-order execution. They need to be examined within the context of memory-centric systems. Okay, so we're always looking for bright and self-motivated students who have a passion for rigorously solving problems, hopefully, and who are willing to do proper justice to scientific exploration, evaluation, and communication. And as opposed to what you may hear, unfortunately, we cherish working with everyone all over the world. There's no, basically we can get students from all over the world and we work with them. There's no discrimination with diverse backgrounds. And I think we have an open and inclusive environment that fosters and values creativity, free exploration, collaboration, and rigor. So if you're interested in all of this, work with us. And we've already covered some of these slides, so I'm not going to talk about this, but you can read more about us in the newsletters. We have actually quite a few of these newsletters right now, starting from 2020. And we have some new alumni. Recently, we've graduated 2 PhD students and a postdoc. They go to different places. Again, I'm not going to go over them, but I'm proud of all of them. And you can learn more about us from clearly many lectures. And this is a recent interview and a bunch of other interviews, etc. Okay, so basically, if you're interested, email me. Take our courses online or in person. I think critically reviewing papers and trying to develop ideas is a really important component. So if we interview, for example, we'd like to see how you're thinking. You may not have a lot of background, but how you're thinking is really important for me, for example. That's kind of thinking is really important. Okay, again, I'm not going to go over this because we've talked a lot about this and we have a lot more to cover, but you can find this information. The one thing I will mention, we have some thesis page online. This is not very up to date. We actually do a lot of work, but it's very difficult for us to keep a thesis page separately up to date. So if you're interested in these general areas, you should just talk with us. Right? And then there's also this opportunistic nature of research. I think a good researcher is always opportunistic, meaning they don't say, oh, I work in these areas only. There's maybe some other area over here, right? That's actually very interesting. And that area may be brought in by clearly exploration. But that could be brought in by new people who may have new ideas or interest in different areas can enable exploration. This is essentially a machine learning system if you think about it, right? You're working in one area, you develop expertise, you keep exploiting that expertise and clearly exploring within that expertise, but then there's some other exploration happens by randomly or somewhat randomly or guidedly choosing some other areas, right? So it's good to think about that. So that's one of the reasons these thesis topics are not up to date. And the other reason is we're busy doing research. We cannot update all of the thesis over there. And some of the thesis just happen naturally. In fact, I think the best research really happens organically. You come and you have some idea, maybe, or you have some topic that you want to work on and you study it, you study a bunch of papers and you say, oh, I have a better way of solving this problem. What is this fetch their instruction prefetching? I can actually do this much more efficiently, right? And that's the kind of research that can have a lot of impact in the end, I think. But that's not the only way of doing it. Okay, so we have an application site, especially for people who are online. But if you're here already, then we can talk to you. Any questions on that? Otherwise, I'm going to jump into parallelism, heterogeneity, and bottleneck acceleration, which is a different topic, but it's a very core topic, I think. We're going to talk more about parallelism after today also, after we finish bottleneck acceleration. But I wanted to do this bottleneck acceleration first because it's going to make all of the other topics go a little bit faster, in a sense. We're going to accelerate some of the bottlenecks earlier, and then we're going to talk about other topics that are related to this a little bit more. I mean, clearly we've been talking about parallelism, but we're going to talk about a specific type of parallelism today, and we're going to try to analyze parallelism. And we're going to be more processor-centric, but the heterogeneity concept itself is not really processor-centric. So this is our agenda. We're going to talk a little bit about issues in parallelism, and then talk about heterogeneous multi-core systems, their evolution. As I said, I was giving this lecture like 15 years ago, and I was talking about heterogeneity. I was actually giving lectures on asymmetry everywhere. You can find some of the slides in the back. And we were doing a lot of work in that area also. And there were clearly people saying that this is complex. We don't want to design multiple cores, etc. But now everybody's designing multiple cores. And there's a good reason for it. There are multiple reasons. I'm going to give you one of the reasons that I believe is very important. One of the general, not just a single reason, but general collective concept of reasons, as you will see. And then we're going to talk about bottleneck acceleration in more detail. These are some of the readings. As you can see, we're going to cover some of these. But let's start with heterogeneity, even before we start with parallelism, because we're going to talk about parallelism later on also. So heterogeneity essentially is, I use the word heterogeneity, but we use asymmetry interchangeably. In my opinion, they have the same meaning, at least for the purposes that we're going to use. And it enables specialization. So I'll contrast heterogeneity with homogeneity and symmetry. Essentially, homogeneous means everything is the same, right? Symmetric means everything looks alike, right? This is really a system design concept, a very general one, like a lot of the concepts we've been discussing in this course, and also a life concept as well. Essentially, the idea is instead of having multiple instances of a resource to be the same, in other words, homogeneous or symmetric, design some instances to be different, i.e. heterogeneous or asymmetric. This is the design perspective. The other perspective is, because I cannot design all of the resources to be the same, I'm going to let them to be different, or I don't have any control, right? You can also think about it that way, right? And we've kind of seen that, right? With the refresh, for example. I cannot make every single DRAM cell the same leakage, so I'm going to live with whatever I have. Now, this is a heterogeneous environment, clearly. There is a lot of heterogeneity in DRAM. What we do is treat it homogeneously, meaning make the refresh equal for everything. What I'm going to talk about is really exploiting that natural heterogeneity. So we have already seen exploiting natural heterogeneity. So essentially, heterogeneity exists in nature. I think of like transistors as nature, but you will see that heterogeneity exists among people also, as you can see, right? The question is, are you exploiting it in a heterogeneous manner? And we have seen that in refresh, retention-aware intelligent DRAM refresh. You refresh the cell according to its leakage. So now that's a method that exploits heterogeneity to gain benefit, which is energy, power, performance, quality of service. But then you can also design things to be heterogeneous. And we have also seen that, right? We've seen, for example, tiered latency DRAM, right? Adaptive latency DRAM. Adaptive latency DRAM actually is exploiting natural heterogeneity, but tiered latency DRAM is really designing a subarray to have two components. One is fast, one component is fast, the other component is slow. Now you added heterogeneity. That's a very conscious design. Right? Okay, so you can design heterogeneity or you can exploit heterogeneity that's already present. Now, regardless of whatever you do, different instances can be optimized to be more efficient in executing different types of workloads or satisfying different requirements and goals. And we've seen this already. We're going to look at a more specific instance. Essentially, the fact that different instances can be optimized for different purposes enables specialization or customization. So why do you want to do this? Essentially, there are two major reasons. We've already kind of seen that also, but I'm putting this into words right now. Different workloads executing in a system can have different behavior. And systems are designed to satisfy different metrics at the same time, right? So the first one, different applications can have different behavior. Different execution phase of a single workload or single application can have different behavior. The same application executing at different times can have different behavior due to input set changes or dynamic events that the application sources, right? There are many examples of this, like locality, predictability of branches, instruction level parallelism, data dependencies. Again, I'm not going to talk about this, but we're going to cover serial fraction and parallel fractions today. Interference characteristics that we may have seen. And also systems, whenever you design a system, you're really trying to satisfy different metrics at the same time. When we design memory controllers, for example, we said we want performance, but we also want fairness. And then we also want low complexity. And you can keep adding more and more, and that kind of leads us to more heterogeneous design, as you have seen. There's almost never a single design goal, depending on the design point. If you remember the earliest lectures, we had a list of metrics, like maybe 10 metrics, but clearly 10 is not enough today. And here, there's more. Okay. So basically, the problem with symmetric designs is it's really trying to fit everything into one type of design, one size fits all. I already said this, to all workloads and metrics you're trying to fit that design. But it's very difficult to come up with a single design that satisfies all workloads, even for a single metric. So assuming you don't care about any other metric but performance, a single design is still not good enough. And we're going to see that today more. Now, this becomes even more difficult when you actually have multiple design metrics. If you want to really get the best of multiple design metrics at the same time, a single design cannot satisfy this. Another example, we discussed, for example, the machine learning inference accelerators, right? We talked about Google Edge TPU, if you remember. And a single monolithic processor-centric design was not able to really cater for many different types of machine learning models and layers. So we decided to add heterogeneity into the accelerators. So we designed 3 different accelerators in that particular case. One of them processor-centric, 2 of them are data-centric. And the goal was to really satisfy different parts of the workload so that you can get better performance and better efficiency at the same time. And we also gained area efficiency, if you remember. But of course, the cost was always complexity. And you need to decide what to execute where. And that's not going to change here also. The cost is going to be complexity, and you need to figure out what different component to use for a given thing, task, for example. Okay, so this holds true for different system components or resources. Essentially, everything can be re-examined to be heterogeneous, and also policies and algorithms. It's kind of like a general principle, right? We've talked about a lot of general principles in this course. Memory-centric computing was one of them. I think heterogeneity is also an all-encompassing principle. If you look at all resources, they could all be heterogeneous. Of course, this will increase complexity, yes. Okay, so let me give you a pictorial example. Again, a picture is worth probably 1,000 words. This is symmetric. This is a slide that I prepared in 2008 or so. You can see that in this case, it could be cores, but it could be anything actually. It's one size fits all. And energy and performance is suboptimal for different workload behaviors, essentially. If your workload needs greater than this box C, for example, too bad. You don't have anything that is greater than this box C. If your workload doesn't need as much as C, it needs 1/10 of the C, too bad. It's wasting resources of the C, essentially. So if you do asymmetric, this is one example where this could be static, or it could be dynamically configured to be asymmetric. Essentially, this enables now customization and adaptation, right? Because processing requirements vary across workloads. You can find that one workload that needs something as big as C1 should be scheduled here. One workload that needs something as small as C5 is scheduled here. Right? Of course, you can actually go even lower, right? Okay, basically, hopefully you can get minimal energy and adequate performance by doing this. Okay, but now you've also seen that complexity increases, right? What is the granularity at which you do this? Is it static? Is it dynamic? So there are a lot of actually interesting questions that open up. Okay, we've already seen examples before. I'll go through this relatively quickly, but something that we have not seen in this course, this is actually a very old principle. If you've taken DDCA, we've talked about vector processing, which is really the core of today's GPUs. Today's GPUs are essentially vector processors. Even matrix vector multiply engines are essentially systolic vector processors, kind of. But basically, Cray1, which was designed to be a vector processor, I guess I have it in the next slide, had actually a scalar pipeline as well, because they figured out this wide vectors are not good for scalar instructions. If you're operating on one piece of data elements, you don't want to fetch 64 of them. Or you don't want to waste 64 functional units for executing an instruction that requires a scalar value. I'm going to show a picture of this you may have seen earlier. So modern processors also have scalar instructions and SIMD extensions, which is essentially very similar to Cray1 design from 1970s. We've seen decoupled access execute in DDCA again. I don't want to go through everything over here, but basically you specialize the access part of the pipeline to memory access, and then you specialize the execute part of the pipeline to execution instructions. All of these ideas are employed in existing processors to different degrees. We've seen thread cluster memory scheduling, so I'm not going to talk about that. RAIDer, heterogeneous latency DRAM, hybrid memory systems, and there are many different types of hybrid memory systems that we have seen also. Heterogeneous cache replacement policies, this is not up to date, as you can see. We've seen hybrid prefetching earlier also. All of those are heterogeneous examples. And these are all employed actually in real systems. And people don't think about complexity as much, right, when they actually do this. Well, they do think about complexity, of course, but they actually make the decision to actually have heterogeneous components. Okay. So this is the Cray 1 picture that you had seen in DDCA, which I find fascinating because this was designed to be, this is the supercomputer of the day, right, 1970s. And you can see that this is the vector processor, which is the major chunk. It has 8 64-element vector registers. You operate on 64 elements at a time. But if you're operating on 1 element at a time, you don't want to use this because it's very wasteful. So they added scalar registers. And this is heterogeneity at the ISA level as well as microarchitecture level. And it's not only that they added those scalar registers, they made that scalar part of the pipeline the fastest of its time because of what we're going to talk about later on today, which is the serial bottleneck. Seymour Cray was a very smart architect. He was more of the, let's say, intuition-based architects who has been designing things. So in my opinion, he's kind of like an architect that can make decisions without requiring a lot of data. This is also good to think about because you cannot predict all the data in the world, right? You're designing a computer for 20 years down the road, maybe. Can you really have data to actually make a decision? That's also true for architects who design buildings, for example, right? They design buildings based on some intuition. Also, of course, there's math, et cetera, involved, but they cannot model everything. It's impossible. Hopefully, they model earthquakes. That's not true in all parts of the world, though. Sometimes they claim they model earthquakes, but then, you know. Okay. So basically, going back, they designed this vector processor. The goal was to execute scientific code fast, which is parallelizable code. But they figured out quickly that the real bottleneck, assuming once you accelerate the vector code, is really the serial part. So the serial part, sequential bottleneck, we'll see that also. We'll accelerate in a different way, but we'll also use the same principle of heterogeneity here. They basically said, oh, we really need to execute scalar code also fast. That's why they designed the scalar pipeline to be the fastest of its time in the 1970s. So it was the fastest vector processor and also fastest scalar processor of its time. Okay, so we've seen hybrid memory systems. We've seen thread cluster memory scheduling. Basically, our goal was to design a policy that's good for different metrics and different threads, if you remember. And we've used heterogeneous policies for that. Again, I'm not going to go through this in detail, but clearly there's a lot of heterogeneity in this policy. Well, there are different policies for each cluster, in fact, right, if you remember. And then we've talked about radar. We've talked about tiered latency DRAM. These are just to jog your memory. These are all heterogeneous designs, essentially. Okay. There's something that we're going to cover in later lectures, which is actually very important. Interconnects. I've been trying to push interconnects earlier in these computer architecture lectures, but sometime we need to figure out how to do that. Interconnects are actually very important because this is part of the communication bottleneck. And there are heterogeneous designs for this also. I'm not going to go over this right now, but depending on the access patterns, communication patterns you have, you may want to have different types of interconnects. For example, this Tylera design from 2000s, early 2000s. If you're streaming data, the communication pattern between one core and another core is streaming. It's much better to have an interconnect that's kind of dedicated to that streaming data. And we'll see that circuit switching is one way of satisfying that. For other data, maybe you need different types of interconnects. Basically, they had 5 different types of interconnects, networks on this chip to deal with 5 different types of packets, cache requests versus responses versus IO versus core-to-core messaging versus streaming, essentially. Okay. There's also examples from real life that we could do a lot of, but I will go through this again quickly. It's abundant in real life. We're all heterogeneous. Genomic variation, for example, right? Also other variations. Cells are heterogeneous. I like this example also. These are specialized for different tasks. You have a lot of different cells. Organs are heterogeneous. Cars are heterogeneous. You can imagine why, right? The buildings are heterogeneous for different purposes. Rooms are heterogeneous, etc. Okay, I don't want to harp on this more. Okay, now let's go into a little bit more. Essentially, asymmetry is really a way of enabling specialization, right? There's always this tension between general purpose and special purpose. And it's always been there. Since computers were being, let's say, implemented, initial computers were actually quite special purpose, right? They used to do signal processing for some tasks. They used to be analog, etc. And over time, people said, okay, we don't want to design a computer for every single task. So general purpose computers started to dominate. But now we're actually back in a, if you look at the historical perspective, we're in a position where probably special purpose is becoming even more important than general purpose. It's already become more important, maybe because of the applications and because of the lack of technology scaling in the general purpose domain. Right? So general purpose has scaled really well because of technology scaling. But then both applications and technology scaling has been pushing general purpose, squeezing it. Now we're actually more special purpose today. So asymmetry is really a way of enabling specialization. It really tries to bridge the gap between purely general purpose and purely special purpose. Purely general purpose, we've already discussed, is a single design for every workload or metric. Purely special purpose, single design per workload, maybe per workload per metric, right? So you could actually have different designs for each workload for different metrics. Okay, so asymmetric essentially kind of is somewhere in the middle. Multiple sub-designs optimized for sets of workloads or metrics and glued together. This is one way of looking at it. And the goal of good asymmetric design, what's happening, is to get the best of both general purpose and special purpose, in my opinion. So let's take a look at the general, overall advantages and disadvantages. So overall, you can enable optimization of multiple metrics, as we've discussed. You can enable better adaptation to workload behavior. You can provide special purpose benefits with general purpose usability and flexibility. That's actually interesting because you have some set of components and they kind of look general purpose, but the compiler, for example, or some system can actually take care of the scheduling. But there are also disadvantages we've discussed, and overhead and complexity in design and verification is unescapable, I think. There's higher overhead in management, scheduling onto asymmetric components. And there's also overhead of switching. If you want to really switch between components, okay, I execute this workload over here, but maybe now it should be executed over here for whatever reason, because it went into a phase that is better fit for this type of core or cache or memory. Now you need to switch, and there's always overhead in switching. There's no free lunch, unfortunately. And these are the three major overheads, I think. Complexity, scheduling or management overheads, and also switching overheads. And we will see this over and over and over in any heterogeneous design. Yes?
You mentioned optimizing for multiple metrics, but the same system, depending on who uses it, might require different metrics.
Yes.
Is there consideration to have this customization? For example, the person who might get into the data side, how fair should be, how performant.
Yeah.
Is that part of the design space?
That could be, right? Certainly, if that input is provided, you can maybe configure the resources to maximize some of the metrics that are important. Right? You still need to have some asymmetric components that you can play with. Right? So then the system or the scheduling or the task management becomes more important. And they have to really be aware of what metrics are required and then do the scheduling. The design can also be that way, but that's a bit difficult, right? If you actually, like you can, one vision is basically everybody has their own computer designed specifically for themselves. This is actually expensive probably. If you have an FPGA, that could actually enable things, but FPGAs have their own overhead reconfigurability. But if you have an asymmetric design, at least you have space for optimization for the metrics. Okay. Okay, another example. This is actually an old example. Today you have general purpose cores, CPUs and GPUs together, right? This shows heterogeneity in execution models and ISAs. In fact, increasingly, we have other things also. But I'm going to contrast this with heterogeneity in only microarchitecture. Basically, microarchitectures may be heterogeneous and something upstream, the compiler or the system, can basically take advantage of these different microarchitectures. Here, the programmer needs to write code potentially differently, right? For CPUs, GPUs, maybe FPGAs, etc. Memory-centric computing also adds heterogeneity to the system, right? So if you have processing near memory, we never propose to get rid of everything else, so it's another accelerator potentially, right? I'll go through this also relatively quickly. Well, we still have time, that's good. Essentially, I think we have three major problems in future systems, and they can all be solved with heterogeneity. We've talked a lot about the memory system. We've talked a lot about efficiency, but we're going to talk a lot more about it today. And there's predictability and robustness we've also talked about. Essentially, heterogeneous designs can cater for all of these, more asymmetric designs. But today, we're going to focus especially on efficiency and especially on performance efficiency, but energy will actually follow in many of our results. And efficiency is always an enabler for scalability, meaning if you're more efficient in the execution of your workload, you can finish it faster, and those resources could be available for something else. Or you could use resources in a much more frugal manner. And then if you have a set of budget, you can execute more things in parallel. So scalability is really a function of your efficiency always. And we're going to see really concrete examples from real workloads today. So today, actually, we have a lot of examples of asymmetric designs. This was not the case in, let's say, 2008 or so. But again, I'll go through this relatively quick. These are some early examples of heterogeneous multi-core. But today, I think everybody's doing heterogeneous multi-core, even in like large general purpose systems, as we will see some examples. Okay, I think we've already seen this picture also. There's increasing heterogeneity in everywhere. And that's going to not change, in my view. So this is a real example. I didn't have this example in 2008 or even 2019 or so. But you can see that there's a lot of heterogeneity in this thing, right? There's the high performance cores over here. There's they don't call it low performance cores because that doesn't sound well, I guess, efficiency cores. And then there's the GPU. And then there's other stuff like neural engine. So there's a lot of both microarchitectural heterogeneity, which is between high performance and low performance cores, or large versus small cores, as we call them. And also architectural, like ISA visible, programmer visible heterogeneity, which is GPUs versus neural engines. And that's true for other general purpose SoCs also. If you look at this, there are large cores over here. I can see that they're large. And then there's small cores over here, more efficient cores. And then there are other engines like media engines. There should be some other accelerators over here that I cannot see right now. Okay. Any questions? Yes.
Dynamically configuring
mm-hmm. Yeah. Mm-hmm. Yeah. Yeah, that's a very good question. I mean, I'm not going to cover some of those things, but that's a very valid question when it comes to heterogeneity, because they could really enable dynamic heterogeneity in a much easier way. I think certainly programming FPGAs or CGRAs is much more difficult in general, right? Whereas if you have a fixed function process, well, I shouldn't call it fixed function, like a fixed ISA. A lot of these FPGAs and CGRAs lack the fixed ISA, and that abstraction level has made programming easier for the masses. I think with FPGA and CGRA, that abstraction level is gone. And that abstraction level, once that abstraction level is gone, you don't have a fixed set of instructions. Now you have to compile your entire data flow program or whatever, high-level program, into the substrate. And we have not, unfortunately, developed good enough flows to enable high performance translation from high-level code to, let's say, circuits. People are working on it. Clearly, there are many people working on it, but I don't think it's there yet still. Yeah. So that's a good question. I don't know. I think, yeah, I'm not sure if the fabric that is designed today is also the best fabric, right? Because if you look at FPGAs, there's a lot of overhead in really design, right? There's a lot of overhead to execute a simple function. And configuration doesn't get rid of that overhead, right? The area is still large. So I think there are issues in multiple levels. Now, the goal of CGRA's coarse-grained reconfigurable acceleration was to get rid of some of that overhead, right? If you have coarse-grained blocks that have much less overhead depending on what you do, you can get rid of some of that hardware overhead for reconfiguration. But I think the compilation issue still remains over there. And maybe figuring out what are the blocks that should be there for CGRAs has been difficult also, right? But these are all great topics, actually. Very interesting topics. In my opinion, yeah, we need to be more efficient. We need to look at more efficient FPGA designs and also look at how to really compile, but that's also a tough problem. This is an area where abstraction actually helped a lot. The ISA abstraction, it's kind of really nice. You have for a compiler, you have a very nice target. Now, everybody at the higher level can target that thing and optimize that thing. Once that abstraction is gone, what do you optimize for, right? It becomes difficult. You need to know the hardware essentially, right? Which is a very interesting concept, but maybe it's an idea whose time has not come yet Okay, any other questions? I mean, even this idea took a long time, right? We'll see this asymmetry in the course. Okay, so let me give you some historical perspective. These are actually slides from older times. But essentially, while I was doing my PhD, people were actually working on multi-cores also, and multi-cores were becoming a thing, let's say, in industry, because scaling a single thread performance was not easy. And people were building multi-cores, and these are simpler and lower power than a single large core, and it enabled large-scale parallelism on a chip. And today, everything is multi-core, of course. But the approach people were taking at the time were actually a more symmetric approach, except for this one over here, which is an interesting exception, which we may talk about when we get to coherence also. So with many cores on a chip, what you want is really scalable performance, ideal scalability. We're going to talk more about that in multiprocessor lecture. Essentially, you want n times the performance with n times the cores when you parallelize an application on n cores. That sounds beautiful. Ideally, that's what you want. This is called linear scaling also, as we will see more. But what you normally get is Amdahl's law. Hopefully people know about Amdahl's law. I'm going to show that. This is really the serial bottleneck. Your parallelization is limited by how much you can parallelize. If there's a part of your code that you cannot parallelize, that really bottlenecks your performance. So you want n times the performance, but 50% of your code you cannot parallelize. Your n can be infinity, and you get 2x performance. And then this is, you can do the calculation over here. 50% of your code is parallelized, meaning 50% you can parallelize an infinite number of cores, that goes to 0. Your 50% remains. So you basically have 100 divided by 52x, right? That's the idea. It's always good to think about infinite parallelization. Now, the problem is not just Amdahl's law. Amdahl's law is very optimistic. I mean, it's a nice way of thinking about, it's a model, right? It's a model of thinking. And not all models are not always accurate, but they can be very useful. Amdahl used his model to argue that, okay, we should really be focusing on single processors. In his 1967 paper, he said, 1965 paper, he basically said, in fact, the title of the paper, it was the validity of the single processing approach. I forgot everything, but I forgot the exact thing. But the validity of single processor approach to achieve large performance capabilities on a chip. He basically said on many workloads you cannot parallelize more than 70%. So we should really be focusing on that, getting that single processor right. If you read that paper, you will see. But okay, assuming you got the single processor right, you parallelize your program 100%. You got rid of the serial bottleneck. Good luck. I've never seen anyone to get rid of that serial bottleneck yet, even though they claim to have done so. There were actually, when GPUs were coming out, what some people were saying, oh, this is great, so we're going to get rid of all the bottlenecks. Well, serial bottlenecks are still there in GPUs. But then there are other things. Like, okay, assuming you've gotten rid of perfectly the serial bottleneck, there are parallel bottlenecks. There are bottlenecks in the parallel portion, which we're going to focus a lot on today. And we're going to see some of that. Okay, so this is Amdahl's law. Essentially, this says your speed up is limited by the parallelizable fraction of the program. We're going to see this more, but before we see this more, essentially you have a parallelizable fraction of a program. N is the number of processors. The speed up you get with n processors looks like this. You can make sense of this. I already kind of calculated with particular values. F was 0.5 and n was infinity earlier. But basically, the parallel portion, you can parallelize. The execution time of the parallel portion can be divided by n. Execution time of the serial portion cannot be divided by anything, as you can see. That's a model. Okay? So this says that basically, as you parallelize your program, parallel portion goes to 0 as n goes to infinity. Right? And your bottleneck becomes f, essentially. Right? So if you take the limit of this as n goes to infinity, you'll get f. Or 1 divided by 1 minus f. Right? That's what you would get. Okay. So basically, it says maximum speed up is limited by serial portion. In the next lecture, I'm going to show you some beautiful graphs. But you can, again, put some numbers over here. F is 99%. That's a pretty high. You would be lucky if you have a program that looks like this. And maximum speed up you get is 100. Imagine you have a 1,000 core processor, you'll get 100 maximum. You're wasting 90% of your cores if that's the case. Okay. And that's not all. Unfortunately, there are bottlenecks in the parallel portion also. It's not usually perfectly parallel. We'll talk about more of these, but there's synchronization overhead. These cores, these things that you parallelize across different cores, they need to synchronize with each other, right? We talked about locks, etc. We're going to talk a lot more about that today. One of them may need to wait for another. Now you're serialized that code. It cannot be perfectly parallel if that's the case, right? Perfectly parallel means there is no synchronization, there's no communication, and you're perfectly parallelized it, as we will see. There's no contention also between them, right? So there are three major reasons why parallel portion is not perfectly parallel, and these are very fundamental. Synchronization, you could also call it communication. Load imbalance, meaning imperfect parallelization. You have one core, you parallelize your code. One core takes 10 seconds, the other core takes 1 second. Why? Because, I don't know, there's some data dependency, and one data is harder to access for one core. There could be many reasons, of course. You have not perfectly divided the work. That could be another reason, right? There could be many reasons. The load imbalance happens because of programmer or the microarchitecture and anything across the stack potentially. And we're going to see that also. Actually, we've kind of seen that when we talked about memory scheduling for parallel applications. Right? And the third reason is we've covered this a lot, which is resource sharing. Right? These things that you parallelize don't execute without interacting with each other. Apart from explicit interaction, they also implicitly interact in the shared resources. Once you have contention, one core can be delayed over another core. You have serialization, essentially. And that contention that we were trying to solve nicely when we designed memory controllers, caches, etc., leads to this this equation to not hold, essentially. So you cannot basically do a simple f divided by n at that point. So this is actually a nice slide that summarizes all of the caveats of parallelism that I know of. If you come up with something else, please let me know. Then we're happy to modify the slide. The slide has been around for 15 years so far. Okay, so basically, let's talk about these serialized code sections. Essentially, many parallel programs cannot be parallelized completely. We talked about sequential portions, serial part. I'm going to give you examples. There's also critical sections that we talked about earlier, locks, essentially. Only one thread can be updating the shared data, and another thread that needs that shared data needs to wait. There are barriers when you actually parallelize your program, partition the work, and all of the threads do something, and when they need to go to the next stage of parallelization, they need to do something else, right? For example, I think one of my favorite examples here, okay, I'll give it today, not tomorrow. You have a program that you've written, and your goal is to count the number of letters in a book, right? One way of writing this program is actually take the book, let's say it's a 1,000-page book, and you're dividing it across 100 processors. Give each processor 10 pages. This is actually very commonly used in parallel processing. It's called the bulk synchronous paradigm of execution. You give a chunk of work to each processor, and let's say you sequentially distribute the chunks. The first 10 pages go to processor 0, the last 10 pages go to processor 99. Not a terrible way of parallelization, right? And then each processor counts the first 10 pages. And then after all of the processors finish, you try to merge the results. So the first barrier you get is until all of the processors finish their pages, right? Of course, you can optimize this, like you can do a subset of processors, etc. But let's assume that it's a first cut at this program. All of the processors need to reach the barrier, so they update their local histograms of the count of every single letter, right? Did I say word? Letter. It should be letter earlier. So you're counting the letters. Now, all of the bottlenecks exist over here. One processor, the first processor, let's say first 10 pages are empty in the book. What does that do? It's done very quickly, right? It reaches the barrier right away. The next processor, unfortunately, gets the most heavy pages. The next processor gets 5 pictures. So it's also easy. So now you've broken the load imbalance immediately in that picture, right? In that task. And this is a difficult task. How do you achieve load imbalance, right? In this task. Think about it. Even the simple problem of counting letters in a book. Okay, and then when you're updating the histograms, like shared histograms, you need to access the critical sections. And then when you're distributing the tasks to different processors, you have a sequential portion. Who distributes the tasks? Do the processors get their task on their own? Yeah, you can try to parallelize it. And then when you're actually trying to solve the load imbalance problem, what might happen is you may actually add more sequential portions. Because if you want to solve the load imbalance, let's say dynamically for some reason, you figured out, okay, my load imbalance was incorrect. It's very hard for the programmer to solve the load imbalance problem in the problem that I described, right? The programmer doesn't know the input. This may be the 1,000-page book. It may have it may have this imbalance. Another book may have a different type of imbalance, right? So basically, if you're trying to solve the load imbalance problem with some dynamic mechanism, you make your program more complicated. You can do task stealing, for example. You basically chunk things in a way such that smaller chunks can be scheduled to different processors. But then you have overhead of managing those chunks right now. So these are all fundamentals of parallel processing, if you think about it. And all of them are limited by all of these serialized code sections. Okay, serialized code sections, if you're serialized, basically your performance reduces, you waste energy, and you limit scalability, as we will see. So let me give you one example very quickly. It's one of the papers that we're going to ask you to read. MySQL is an open source database. It's relatively old right now, but people still use it. You open some database tables and you perform some operations. You don't need to know exactly what these are, but this part of the program is parallel. This part of the program is more, let's say, critical section based. You need to access this open tables cache, which is really shared across a lot of processors. And whenever you really open a database table, you need to mark it as I opened this database table, so nobody else should really change it, right? So you have actually, you're going to write to this table. So there's a critical section that protects it. Again, the paper has some more detail, but this critical section really limits your performance. As you add more processors, meaning increase your chip area, let's say, your speed up increases until some point, and then after that point, it starts reducing. And one of the major reasons the speed up starts reducing is processors contend for this critical section. This critical section becomes a bottleneck. I will show you that using simple asymmetric designs can actually increase this. This is an unoptimized version. Basically, you can scale up. This is called a scalability curve in parallel processing. Essentially, you're computing the speed up compared to a single processor version of multiprocessor versions. And this is where the performance scales up to. I don't know what that core is, but 16 cores or so, right? 16 core area equivalents. With an asymmetric multiprocessor, you can do much better baseline. Okay, we'll see more examples. Okay, so let's take a look at what fundamentally do we want, right? Fundamentally, in a serialized code section, you want a powerful large core. Yes? Yeah. This example, okay? Symmetric cores, yes. Exactly. You get worse performance because your bottleneck is really the critical section. And what happens is you're really ping-ponging data. We've discussed ping-ponging in an earlier lecture. We're going to see more. But you're really ping-ponging shared data as well as locks across the processors. There's also contention effects that was also taken into account here, but that's not the major reason why the performance goes down. But this is a very common curve. I mean, in asymmetric also at some point, you would go down, but maybe not at 32 for this workload, right? Okay, that's a very good question. So basically, we want, in a serialized code section, you want a powerful large core. The question is, what should that powerful large core look like? In a parallel code section, we want probably many wimpy small cores, right? Depending on the code section. If you parallelize it really nicely, wimpy small cores could be good. And these two clearly conflict with each other, right? If you have a single powerful core, you cannot have many cores. And a small core is much more energy and area efficient than a large core. So this is what we're going to assume. A large core is a large out-of-order execution core with a lot of techniques for instruction-level parallelism and memory-level parallelism. Small core is very simple in order. I'm going to show you more examples of this. Maybe not even a branch predictor, right? It may have fine-grained multi-thread. And this is kind of a rule of thumb. It's not, of course, correct for every workload, but this is kind of an assumption that we're going to make for some calculations now. Large cores are power inefficient. Essentially, you get 2x performance with a large core for 4x area. Area could be a first order thing for power, let's say, a predictor of power. And these are some results from Intel, actually. This is their paper in 2004. They basically talk about large versus small cores in a different context, as we may see later on. But this is what looks like a large core over here. And this is what looks like a small core. You can see the pipeline with pipeline depth. You can see the normalized performance. I think they're quite optimistic over here with a 5 to 8x. Normalized power is much larger, and normalized energy per instruction over here. So basically, large cores are not very efficient, but they do get high performance. Even I'm not sure about the 5 to 8x. I don't know what code they're running. Okay, but when multi-core systems were being designed, this was one of the earliest multi-cores, actually. IBM put together a very nice multi-core system in 2000, earlier than 2002, actually. It's a symmetric multi-core chip. Basically, they added 2 powerful cores. This was one philosophy. We're going to keep the cores powerful, but we're going to have few powerful cores. And you can see some of the parameters of the score, which we'll not go into in detail. We've already seen the stream-based prefetching that they employed, actually, in IBM Power 4. But this is, for that time, it's a pretty powerful core. Many cores did not even have 8-wide instruction fetch at the time. IBM Power 5 made each core a little bit more powerful, and they added multi-threading, simultaneous multi-threading. So that was the philosophy, essentially. There was another philosophy, which was Sun, as we've also discussed. These guys were bought by Oracle, unfortunately, as you remember. So they were innovating quite a bit, actually, but they stopped innovation. That's very sad. A company buys another innovative company and makes it non-existent. That has happened multiple times also. I think more recently it happened with VMware versus Broadcom. Broadcom bought VMware, and VMware is dead now, kind of. Yeah, meaning the innovation is dead. So it's good to think about also those things. So if your company gets bought, that doesn't mean innovation in the company will continue. That actually happens in a lot of startups also. Some big companies buy startups to maybe kill the innovation because they're not competitors anymore, right? Okay, it's good to think about it. Sometimes maybe not all systems are designed with good principles in mind. Okay, anyway, going back, Sun, these guys were, actually Sun was a very innovative company that a lot of innovations before this also. But they were designing these simple wimpy core processors. If you look at these cores, they actually had 8 processors over here. Each processor was 4-way multi-threaded. And if you look at a single processor, it's very simple. It's 4-way fine-grained multi-threaded, 6-stage, dual issue in order. There's no branch prediction. There's very little data dependency checking because at any given time you have you don't have 2 instructions from the same thread in the pipeline. So there's no need to predict branches. There's no need to do data dependency checking. This is basically fine-grained multi-thread, as you can see. It even had a shared floating point unit among cores, and that turned out to be a bottleneck. So they actually replicated in the next instance of Niagara 2. So this is a very different design philosophy, as you can see, right? It's very simple cores, but many of them. And they claimed this was good for, let's say, their commercial workloads. But over time, they figured out, okay, maybe this was not that a good idea. So let's improve. Let's make cores more and more powerful. And that's why they were going with run-ahead, for example. They added run-ahead to make each core more powerful. And then they were actually adding this simultaneous speculative threading that I mentioned when we talked about run-ahead to make each core even more powerful. So they figured out these small cores were not really that good in the end because of the bottlenecks. Okay, but ideally, we don't want essentially either extreme approach. Like, what do we want? And remember, these are our demands, right? And we've already said everything over here. The question is, can we get the best of both worlds? Let's take a look at best of both worlds a little bit. So we're going to make some assumptions over here. Small core takes an area budget of 1 and has a performance of 1. Large core takes an area budget of 4 and has a performance of 2. This is the tile large approach like IBM and also other folks. As you can see, these are some early multi-core processors. You get high performance on single thread, serial code sections. You get 2 units of performance. But you get low throughput on parallel program portions, 8 units. Why is it 8 units? Because you have 4 cores and you have 2 units of performance, so you have 4 times 2, right? 8 units. Tile small approach, you tile many small cores. In this case, because of the area constraints, this is area 4 by 4 is 16 base core area, and this is 16 small cores now. Some folks also had this idea. Tyler, we discussed that it was actually ultra small cores. Intel had actually a very interesting project at the time, which unfortunately didn't go through. Their goal was to actually have many x86 small cores to compete with GPUs. Unfortunately, their software stack was not optimizable as easily, so they couldn't compete with GPUs, and this project kind of not died, but kind of transformed into something else that is not as influential at this point. But the point is there was a lot of innovation going on also still. So basically, if you look at this, there's high throughput on the parallel part. If you're parallel, you get 16 units, right, that is working for you. But unfortunately, on the serial part, you get a single thread working on a small core, so you get 1 unit of performance. So your parallel part performance is high, but your single core performance is 50%, right? Okay, so basically, we've already said this, right? This is kind of putting everything in the same slide. Tile large has benefits on single thread, but low throughput on parallel portions. Tile small has high throughput on the parallel part, but low performance on the serial part. And one of the reasons why major companies didn't want to go tile small is you get reduced single thread performance compared to your previous processor, right? Single thread processor, because large processors were there already. So the idea is very simple. You can kind of guess it based on the context of the lecture. Have both large and small cores on the same chip. This is performance asymmetry. So that's what brings us to asymmetric multicore. I'm going to give you some examples, and then we're going to take a break. But in one incarnation, you can provide one large core and many small cores. This is one example, right? You carve out 4 small cores and make it a large core. You can do it statically. Static is easier. You can do it dynamically, and people have actually looked at how to do this dynamically. It becomes complex, but it's possible to do. There's a paper called Morph Core in Micro 2012, if you're interested in that. Before that, there was a paper called Core Fusion in ISCA 2007, which are actually very interesting ideas. But statically, it's easier, clearly, right? You can design a large core statically and maybe multi-threaded. Okay, so if you do this, you can extract the serial part using the large core. So you get 2 units in serial code sections, which is the same as tile large. And you actually get 12 plus 2 units in the parallel code sections, 16, almost 14, which is almost 16. And if you actually play tricks in the large core and have multi-threading, you can actually almost get 16. So we didn't play tricks. So we're not gonna assume multi-threading in the large core, but you could actually assume that, and you're gonna get the best of both worlds almost. So basically, if you want to extract serial bottlenecks, whenever you have single thread, execute on the large core. And whenever you have many threads, basically schedule them on the small cores, regardless of your parallels. And then when you get back to a single thread, let's say this is the parallel part, this is the serial part, you go back to the large core, right? That's the idea. Now, if you do this, I've already given you these results actually, right? So tile large, tile small, and ACMP. ACMP gets essentially the same serial performance as the tile large approach and almost the same parallel performance of tile small. As I said, this could be increased to almost 60 with multi-threading. We're not assuming multi-threading in the large core. If you assume multi-threading, maybe these can be, you could get 4 units of performance over here, right? Okay. And I think multi-threading is the right approach actually, but we want it to be actually harder on the asymmetric side. So if you modify Amdahl's law for an asymmetric multiprocessor, serial portion is executed on the large core, parallel portion is executed on both small cores and large cores. And L is the number of large processors, S is the number of small processors, and X is the speed up of a large processor over a small one. Now this is what you get. Now 1 minus F, it gets divided by X over here. Our baseline is a small core, of course, right? Whereas this gets divided by something more complicated, which is the number of small processors times X times L, which is the number of large processors times the speed up that you get. But if you assume multi-threading, this needs to be modified a little bit more. So now you can actually draw curves with Amdahl's law, which I'm not going to do. Okay. Other parts of the code actually can also benefit from a large core. For example, critical sections that are contended, parallel stages that take longer than others to execute, they can be shipped to the large core, right? If you have a large core. And we're going to see that. And the general idea that we're going to examine in the rest of the lecture after the break is dynamically identify code portions that cause serialization and execute them on a large core. So this is a good place to take a break. We're going to look at like progressively different ideas, starting with a small one, which is extracting the serial bottlenecks only, and then do it more dynamically through hardware, software, co-design. But when we talk about these, it's always good to think about, we have looked at one way of doing this, which is really software has a lot of information, provide that information to the hardware, which I believe is the right way of doing it. But clearly, this is not easy to adopt, right? Whenever you modify both software and hardware, you may be able to modify nothing in the end. There are other ways of doing it potentially, like purely in hardware. Purely in software, people have also looked at after our works, but that's a bit harder, I think. So we're going to see a lot of ideas, so hopefully you'll think maybe more ideas. But now let's take a break. I'll take questions after the break. Let's take a break until 14:45, 16 minutes, and then we'll continue. Okay, I think we're right on time. We have some nice snow coming down. In this room, you can see the snow. Who here prefers this room over the other room? Who prefers the other room? You know which room I'm talking about, right? The 16.2. Okay. Okay, you prefer the other room, some people. But I think the majority prefers this room for some reason. Let's see. Is the air quality in the other room okay still? Or I heard some people complain about it earlier, but maybe. Oh, from that room? Or this? Oh, okay, I see. I see that. Okay. More sequential processing here. I see. Is that a big problem? Could be, depending on the situation, right? Depending on the workload you're executing. Yeah. Okay, well, we have heterogeneity in the rooms. Thursdays here, Fridays there. Okay, so now let's jump into some ideas. I'm going to cover a bunch of readings. Let's see how much we can cover. But this is the caveats of parallelism. Remember, we talked about the serial bottleneck. We're going to start with the serial bottleneck. And I've already given you the idea, actually. But we're going to actually execute the parallel bottlenecks as well. And we've already covered this slide. I'm going to start with the first idea, accelerated critical sections. This is a hardware-software co-design to accelerate critical section execution. But let me give you something that will motivate this. This kind of picture is always good to motivate things. Even though you may not have exact numbers, you may reason about things. Right? For example, let's take a look at a code that has 12 iterations, and 33% of instructions are inside a critical section, which is only one thread can be in the critical section. That's all you need to know to look at this. If you execute this code in one processor, P equals 1, the execution looks like this. The critical section is the red part. Now, if you parallelize it in two processors, you can parallelize the parallel parts, but only one thread can remain in the critical section. So based on this, this is what you would see. Right? But you still get pretty good speed up, as you can see, right? Now, if you parallelize a little bit more on three processors, this is what you get. Again, parallel portion can be executed in parallel, but red parts cannot be executed in parallel. Red parts are serialized, as you can see, always. So you get some more speed up, but not as much as going from 2 to 3, actually. Now, if you execute in 4 processors, you get no speed up. And the reason is when you were at 3 processors, when you were at 3 processors, there was no room for parallelizing the parallel part even more by adding one more processor. If you look at this critical section, there's always one thread that's executing the critical section at any point in time, right? And this is an optimistic example, meaning when you go from 3 to 4, your performance doesn't degrade. In many real cases, your performance actually degrades because basically the reason your performance cannot improve is because you cannot parallelize the parallel portions because you're limited, you're bottlenecked by the critical sections, as you can see. So threads basically weight more. Here, this thread, even though it finishes at this point, it cannot enter the critical section because the 4th thread that you added is in the critical section. Same happens over here. So you basically have some waiting time that happens in each thread because you're really bottlenecked by critical sections. And this is if you're lucky, as I said. In most cases, your performance actually degrades. And the reason is now you're communicating more across different threads, right? Whenever you want to enter a critical section, you need to take a lock. Whenever you access the critical section, you access some shared data. And that needs to be communicated across more processors now. And these processors have their own private caches. So there's this ping-ponging effect that we discussed last time, and we're going to discuss more. So even this is an idealized case. So basically, if your performance is limited by critical sections, and if you accelerate critical sections, this is what would happen. With a single processor, let's assume you have some magic mechanism that accelerates critical section by 2x. In a single processor, you get some performance gain, that's good. In 2 processors, you get some performance gain, that's good. In 3 processors, you get some more performance gain. And now the realization is that with 3 processors, you're not always in the critical section at any point in time. Right? So there's room for more parallelization. If you parallelize more, you get more performance improvement, as you can see. And this performance is, at least in this cartoonish picture, better than 3 processors, right? And you're still not bottlenecked, so you could actually parallelize even more. So this is a nice intuitive example that shows that, yeah, I've already shown this part, I already said. Accelerating critical sections actually increases both performance and scalability, right? Scalability, to define it more rigorously, it's really the number of threads at which your performance saturates, becomes maximum. This could be expressed in terms of number of thread, number of amount of area, etc., as we will see. Okay, so hopefully this motivates. Contention for critical sections leads to serial execution of threads in the parallel program portion. Contention for critical sections increases with the number of threads and limits scalability. This was the data from my SQL I showed you over here, right? I'm not going to repeat the same thing, but basically, this is the reason your speed up starts degrading significantly after, I think, 16 areas. It could be 17, don't quote me on it. As you keep adding more threads in MySQL. And we're going to get something like this. And you kind of already know the idea, I think. So basically, the case for asymmetry is execution time of sequential parts, critical sections, which we're going to focus on, and limiter stages must be short. And you can say, it's always good to actually, when we were doing some of this work, some of the comments that we received was, this is programmer's responsibility. Right? Programmer should do this. But it's very difficult for the programmer to do all of this, actually. First of all, programming is difficult. And then getting the programs correct is difficult. Getting a single thread program high performance is difficult. Now you want the programmer to get the parallel thread performance high and also scalable. Keep adding threads and you're going to scale. And there are many reasons of it for it, actually. First of all, it's difficult, right? The second is, maybe the programmer doesn't know exactly about how to optimize a program, right? They need to really be domain experts to optimize a program. For example, some companies, like I'm going to pick on Oracle again, some database companies actually hire a lot of programmers, some expert programmers, who try to minimize these critical sections as much as possible. And they've been doing this for many decades, 3-4 decades or so. And they're still doing it. Meaning this is a difficult problem, actually, even when you have domain knowledge and even if you actually improve the domain knowledge, because it's just the nature of communication and the nature of synchronization across threads. On top of this, there's variation in hardware platforms. Okay, you may optimize for this hardware platform, but another hardware platform has different kind of caches, different kind of synchronization instructions to do the locking, etc., different kind of processors, and then your critical sections become different bottlenecks, potentially, right? It's very difficult for programmers to take into account. Limited resources, meaning what should the programmer really be doing? It's a good question. And on top of this, there's a performance debugging trade-off. Yes, you can always get more performance at the expense of more bugs. And synchronization, this sort of synchronization across threads is one place where you're almost guaranteed to get bugs. How many people have done parallel programming here? Okay. How many people never got any bugs with parallel programming? Hopefully, you're not brave enough to raise your hand, but you can be. But it's very difficult, basically. It's not, it's easy to get bugs over here. How many people have written operating system kernels where they had to really, let's say, synchronize across shared resources, across different threads, allocate resources? I'd recommend thinking about that. Not easy, basically. So you can always get performance at the expense of more bugs. Another way of looking at this is, if you actually have a mechanism that provides you better parallel performance underneath, the programmer can be more liberal in the sense that they could say, okay, I'm not going to do aggressive things that will cause bugs, but hopefully I'll get better performance, right? That's the idea over here. So you're debugging, you alleviate some of the performance debugging problems. So basically, that's why having mechanisms that aid the programmer is much better. Essentially, a mechanism to shorten serial bottlenecks without requiring programmer effort. With programmer effort, you can hopefully do better, but we should aim for these mechanisms in general. This is true for processing in memory, right? One of the issues we discussed with processing in memory is the programming effort, right? Ideally, you would like to minimize the programming effort. Okay, so basically the idea in this work is to extract serialized code sections by shipping them to powerful cores in an asymmetric multi-core processor. Okay, let's take a look at what this idea looks like. Hardware and software cooperatively ship critical sections to a large, powerful core in an asymmetric multi-core architecture. And the hope is that the large core can execute the critical sections much faster. And hopefully that reduces serialization due to contended locks. It reduces the performance impact of hard to parallelize sections. And hopefully the programmer doesn't need to heavily optimize the parallel code. You get fewer bugs and improved productivity. So it has higher level benefits also. And all of this is conditional upon the large core, powerful core executing the critical sections much better. So now there are actually interesting questions over here. Can you customize the large core to be much better at critical section execution, right? We didn't do that as much, but I think there's opportunity here also. And maybe different types of code should go to different types of cores, right? So I can actually specialize this. We're going to use general purpose cores in this, but you can actually, I think in the ideal incarnation of this, you really want to specialize as much as possible to the critical parts of the code. Maybe non-critical parts of the code can be executed in parallel processors that are wimpy. But critical parts of the code, those are the parts of the code maybe where you really want to actually accelerate things, right? Assuming you can determine them. So this is the idea, essentially. You have a large processor and a bunch of small processors. And you have a critical section request buffer. Large processor, in the extreme version of this idea, is dedicated to executing only critical sections and also serial parts. Basically, it's a server processor. You send to the server processor things that are critical. You can think of it that way. And all of these are clients, if you think about it. And the communication model is kind of like that also, right? So basically, normally you have an enter critical section and the leave critical section, which enter critical section actually gets the lock and leave critical section releases the lock, assuming you're doing locking. But clearly you can do other types of critical sections like semaphores, etc. And then there's some code in the critical section. In this case, you're inserting into a priority heap, which may take some time depending on the shared data, right? So what we're going to do is processor 2 executes this enter CS. We're going to add an instruction called critical section call to the ISA, instruction set architecture. And processor 2 sends this critical call section request to the CSRB. Essentially, it's a message saying that I want my critical section to be executed on you, right? CSRB is a critical section request buffer. And then at some point, processor 1 schedules that over here. It could be a FIFO queue. We're going to change that queue later on. In this particular incarnation, it's a FIFO queue. And processor 1 executes the critical section. And once it's done, it sends the critical section down signal. And processor 2 can continue. Hopefully that makes sense, right? It's a simple execution model. It's very similar to what we've seen in Tesseract, for example, right? It's remote function call. You're doing a remote function call, especially for critical sections. And you need to provide all the mechanisms to enable this, of course, right? So let's take a look at an example of this in the programming model. Compiler can actually translate everything, of course, especially if you're programming nicely with libraries to do locking and unlocking, etc. So this is what's executed in a small core lock. You acquire the lock, you execute the critical section with some input data that could be generated in a shared, in a non-critical section, And then once it's done, you unlock and then print the result. This is one example, right? Now, what small core does in the accelerated critical sections model is, this is one way of doing it. There could be other ways. We're going to communicate between small core and the large core through the stack, shared memory, essentially. It computes A, which is the data that's computed in the non-critical section. It pushes the value, input value of the critical section function call onto the stack so that the large core can obtain it by doing a pop from the stack. And then it basically sends a critical section call request for this particular critical section, lock X, let's say. And the critical section starts from target program counter. This is the program counter at which the large core should start executing when it decides to start executing that critical section. So this gets sent over the interconnect. You send the X lock, which is the critical section ID, in other words, target PC, the stack pointer, and the core ID. And then this waits in the critical section request buffer in the large core for some time, hopefully not too long. But if your critical sections are content, actually, it could be too long, right? If you have a lot of contention for your critical sections, everybody can be sending requests to the large core. But at some point, the large core decides, I'm going to execute this critical section. It takes it out of the FIFO queue, and it starts executing, basically, from target PC. And target PC code is modified. This critical section code is modified such that you acquire the lock, just in case, because you really need to maintain the semantics of acquiring the lock. And then it pops the input. So if there are multiple inputs, you need to send, of course, multiple inputs. You need to push all of them, and you need to pop all of them. And then you execute the critical section, and then push the result on the stack. You release the lock, and then execute a critical section return instruction, which communicates a critical section down response to the small core that initiated this request. And then the small core pops the result of the stack and prints the result. Looks good, right? So if you're really executing, if you're really programming nicely, this could all be done by the compiler. Clearly, you could all do this as a programmer as well, right? Now the question is, can you do this purely in hardware? That's a tough thing to do, I think, but potentially doable. And people have tried, but one of the issues in hardware is you need to have some instructions that are actually directly locking. A lot of hardware today actually doesn't have lock instructions necessarily. They execute a sequence of instructions that do locking. This is some food for thought, basically. How do you identify a critical section, basically? Remains a problem still. We may talk about that more in later, essentially later lectures. Okay, so this sounds good though. It's doable, clearly. So one of the issues that you run into if you do this sort of thing, whenever you decide to execute critical sections on a single core or a server, let's say, actually there was some later work that did this purely in software and across different processors, which showed results that look kind of similar to what we did in simulation. One of the issues that you run into is large core can become bottlenecked, right? If you send too many requests to the large core, you can have bottleneck. Now, this may be okay if all of those requests are for the same critical section, for the same lock. Lots of processors are trying to acquire the same lock. They should be serialized because they're going to be serialized anyway, right? In fact, it's better that they're serialized on a large core with large caches because the critical section lock always remains on the large core, right? That's one of the other benefits of executing critical sections in one place. Lock remains on the same place. It doesn't get ping-ponged. Shared data that you're accessing remains on the same place. It doesn't get ping-ponged. So we actually solved the ping-ponging problem. But it comes at the expense of false serialization, meaning independent critical sections can get sent to the server processor. Now the problem is what happens if you have independent critical sections? Essentially, a critical section B can be waiting for critical section A to execute. And these are completely independent. If they were executing on their local small processors, they would be parallelized completely. Right? Now we're serializing them. Very bad. One way of handling this is, actually there are multiple ways of handling. One is doing multi-threading on the large core, right? Meaning you execute critical section call A concurrently with critical section call B by doing multi-threading. And we do that in some later works. That actually alleviates the problem. Now, the downside is you're not using the entire large core to accelerate a single critical section. Right? So each of them can be accelerated less, but maybe it's better than false serialization. So in this work, we have another mechanism which keeps track of how often this false serialization happens. So this is the critical section request buffer. It gets input from small cores. It executes the critical section on the large core. And we have some counters, saturating counters to keep track of how many times a particular critical section was falsely serialized, meaning it had to wait for the large core because some other critical section was executing on the large core. So you get a critical section called A, something happens. You basically decrement the counter because this can be executed. You get a critical section called A, Serializing these is fine. In fact, that's exactly what you want. So you get decrement the counter. Now you get a critical section called B. Unfortunately, this gets serialized, assuming this is a FIFO queue again. You increment the counter. Now, once your counter is larger than some threshold, large core says to the small core, don't send these critical sections to me. And the small core stops sending the critical sections. That's one way of eliminating false serialization, right? You can have a combination of multi-threading plus that, of course. Okay, so keep that in mind. So essentially, the pluses, you get hopefully faster critical section execution. I'm saying hopefully, because the assumption always is that large core is faster. But always think, if your bottleneck is really memory, maybe large core is not that much faster than the small core. It's good to think about it. It's still probably faster, but maybe not that much faster. If your bottleneck is really computation, large core can go really fast, of course. The other benefit I already said, shared locks stay in one place, so you get better lock locality. That's actually a big benefit, and we demonstrate in the paper. Once you read the paper, you will see that some benefit comes from making the critical section faster. Some other benefit comes from actually keeping the shared locks and also shared data in the large core's caches. You get better lock locality, better shared data locality, less ping pong. Yes? Could you say it again? Why do you even need locks? Okay, that's a very good question. Basically for correctness purposes. The reason, okay, so we acquire the lock over here, essentially. We discussed this in a footnote in the paper, but there could be, actually there are two reasons. One is false serialization. Once you have false serialization, you still need locks to execute. So there could be some lock executing here, another lock executing here for the same critical section, potentially. And the other reason is really correctness purposes. We don't want to eliminate locks because we cannot maybe guarantee that someone else may not be executing the critical section, because there is a large view of the system, right? There may be some other code that's written by someone else that may be locking, right? Potentially, yes. Yes, that's right, exactly. But yes, if you're extremely aggressive, you can get rid of the locks also. And that will actually buy you even more performance. Okay, so minuses. In this particular work, we dedicated the large core for critical sections, meaning your parallel throughput reduces. You may decide not to do that, but then you have a problem, right? You want to accelerate critical sections, and you're executing some other things on the large core, meaning those things contend with the critical section execution. Right? So that's the reason why we decided to dedicate critical sections. But we will see that there are other things you can accelerate in this large core when we go to the next work. Clearly, there's some transfer overhead, right? You're transferring the critical section. You're doing a remote function call. You need to send the critical section call and critical section down signals. We're going to analyze those trade-offs a little bit. And then there's also some other thing that needs to be transferred, which is the thread private data, meaning data that you input to the critical section that is generated outside the critical section. This is different from shared data. This is not data that's shared. This is really the data that you're inputting to the critical section to do the computation on the shared data. This becomes worse, meaning it needs to be transferred to the large core. And in this particular case, we did it through push and pop instructions, as you can see over here. There could be other ways. You could directly send data into registers, etc., but that complicates the communication paradigm. But essentially, now you're trading off shared data locality with private data locality. If you had executed the critical section in small cores, private data doesn't need to be transferred anywhere, but shared data now ping pongs. Now the question is, which one's worse? And the answer is it depends. So that's actually an interesting analysis I will show you now. So these are the performance trade-offs. With accelerated critical sections, you have fewer parallel threads because we're dedicating the large core for critical section execution. But on the upside, we're accelerating the critical section, hopefully. Right? So this is the trade-off. What we see in results, unless you're extremely area constrained, accelerating critical sections offsets the loss in throughput. There's another benefit over here, or trend. If you keep increasing the number of cores on chip, the fractional loss in parallel performance decreases, because hopefully you're not going to dedicate a huge fraction of your chip to the large core for mainly design constraints. It's very difficult to design a large core that occupies a huge area of the chip today, as you've seen in all of the pictures of today, right? Today, even large cores are a very small fraction because people don't know how to design extremely large cores that can take advantage of a large fraction of the chip. So basically, increased contention for critical sections also happens as the number of cores increases. So this trade-off actually is good with technology scaling. It's better to dedicate a large core for critical sections, which can accelerate critical sections. Something is happening here. Okay, the second trade-off is you send CS call and CS down signals as opposed to locking and unlocking. We're still locking and unlocking, but we're adding some more overhead. Essentially, okay, I should say that we're still doing locking and unlocking. Basically, you get better lock locality, right? We're adding CS call and CS done. That's additional overhead, but we also get better lock locality. And essentially, we avoid ping-ponging of locks. So there's clearly a trade-off over here. And then let's take a look at the last one. If we get more more cache misses for private data because we're communicating that, because it's the private data is actually produced in the small core, and it has to be transferred to the large core, right? But we hopefully get fewer misses for shared data because now, assuming you execute all of the critical sections in the same core, the shared data always remains there, right? It never needs to be communicated somewhere else. Okay, so let's take a look at cache misses for private data. Usually, the cache misses for private data is actually a smaller fraction, but not in all cases. It depends on how much the programmer optimized the code, etc. In some cases, the programmer has a large critical section, and lots of things are private data inside the critical section, etc. Okay, so let's take a look at one example over here. If you're trying to add, for example, a node to a heap, the shared data is the priority heap. Private data is hopefully one element. Assuming your shared heap is large, when you add this private data, you actually touch a lot of shared data, as you can see, right? In this particular case, we touch 6 shared data nodes, while we touch only 1 private data node. So in this case, keeping these 6 in the cache always, as opposed to ping-ponging a subset of them, is probably better than keeping the private data in the cache. Right? So this is a case where communicating the private data or keeping the shared data, the benefits of keeping the shared data on the large core outweighs the downsides of communicating the private data. But of course, this is not always the case. If you're adding a huge thing and your shared data is small, then there could be differences. Okay, so basically cache misses reduce if shared data is great, or touch shared data. The shared data that you touch is greater than the private data that you touch. Okay, this problem actually can be solved. We're going to see that. There are actually interesting things that can happen. It actually becomes a more general problem, as we may see, depending on the time. I'm going to talk about that paper. Actually, I really like this paper. This is actually applicable to, I think, a lot of communication that happens across threads. So hopefully we'll get to it. Okay, let's take a look at the performance of, yes, please. Yeah. Mm-hmm. Depending on the workload, you choose whether you want to share that data or share data. You mean ship the critical section or not ship the critical section? Yeah, potentially, yes. I think if you understand your workload, well, potentially. Yeah. And we're going to kind of see that in the next work. We're going to try to really identify what should we really ship to the large core. In this case, we blindly ship all of the critical sections except for the false serialization hack, let's say, that tries to fix a problem. But in the next work, we're going to really be more methodical about what should really be shipped there. We're going to collect more information about critical sections. And you could also do more, as you will see. Okay, so let's take a look at the results. So this requires a lot of simulation. And Onur, who did this work, which is part of his thesis, did a lot of simulation. It's not easy simulation in general. So basically, we're going to compare to this symmetric small core processors, an asymmetric multi-core processor that looks like this. We've already discussed this, but large core here in the ACMP, large core executes the serial parts of the code, but not the critical sections. Serial part is accelerated over here. Here in accelerated critical sections, ACS, large core executes both the serial parts, because that is actually good, as you will see in the results in general, and also accelerates the critical sections with the mechanisms we discussed. As I said, it's simulator development actually takes a lot of time for this sort of work. And you can see more in the paper, but these are the large core versus small core parameters. We kept the frequencies equal, but That doesn't need to be the case, but the main benefits of the large core is essentially large caches and also large instruction windows. And there's an on-chip interconnect that you need to model nicely. Okay, and we have 12 workloads that are critical section intensive. Okay, so let's take a look at these results. So it's always important to classify your workloads here. There are some workloads where the programmer was lazy, let's say, or the programmer was a regular programmer. And there are some workloads where the programmer was less lazy, meaning here you have coarse grain locks. And here you have fine grain locks. Fine grain locks are always harder to do because you run into the problem of debugging, etc., and getting it right. Coarse grain locks, you start your program, you write it, you lock everything, and your entire program is a single critical section. That's the laziest programmer. Terrible idea, of course, right? Even that you can parallelize in hardware. Like later, probably not today, but maybe in later lectures, there's this nice idea of speculative lock collision, speculative parallelization. Basically, the idea is programmer was probably conservative when they actually placed the locks. So in hardware, let me speculatively execute the critical section. It's kind of like run-ahead execution. When you see a lock, don't stop, checkpoint the architectural state, and keep executing. But not exactly run-ahead. The goal is not just prefetches. You could also do prefetches with run-ahead. But the goal is to really buffer results. And after you execute the critical section, if no one really conflicted with you in the critical section, just assume that you executed everything in the critical section. That's the idea. That's called speculative lock collision. It's a beautiful idea, I think. It adds complexity of speculative execution, more than run-ahead execution, actually, because you need to keep the results buffered, etc. But even if you have a conservative lock, you could actually accelerate this. Accelerated critical sections are something different, and there are actually trade-offs between the two. Okay, so I'm giving you some other ideas you can see, right? You can read the Micro 2001 paper on that topic, speculative lock collision. So let's take a look at the results over here. Here, we're going to look at a chip area of 32 small cores. SCMP, symmetric CMP is 32 small cores. ACMP is 1 large and 28 small cores, basically. So you lose some parallel throughput with ACMP, of course, and also with ACS. But the overall, especially on programs that are not optimized, and also I should also say that this is really important. We have equal area comparison, but for each system, like the baseline, and when you accelerate the sequential kernels, and when you accelerate the critical sections, we pick the number of threads to be the best number of threads for a given system and a given workload. Meaning, for example, the number of threads that is best in the baseline system may be 5 for a workload, even though you have an area 32. Because the workload is not scalable in the baseline, right? If you actually, whereas the number of threads with ACS could be 10. Right? That's the best threads. Now, if you compare both of them at 0.32, meaning if you actually execute 32 threads in each, the performance improvements of ACS is actually potentially much larger. But that's not necessarily a fair comparison. Right? I mean, you could argue what's fair and what's not, because now you need to pick the best threads in a given system, which may be a difficult problem, as later works and previous work showed. So this is what we did for fair comparison as much as possible. And I'm going to show you some scalability results that show that. So basically, if your workload is not optimized, if you have a lot of coarse grain locks, you get a lot of benefits over here. So the light blue bar or turquoise bars over here show this acceleration of the sequential part, like the serial bottleneck. So you get a lot of benefits even by accelerating the sequential part, right? On average, not a lot, but there are some workloads that gain a lot. And there are some workloads that lose slightly because you lose performance on the parallel part. And these are actually more parallelizable than others. But accelerating critical sections buys you a lot more performance on top of accelerating serial parts. So that's good, hopefully. But you can see that the benefits are lower if the program has fine-grained locks, but they're still not negligible. So there are some workloads where you get about 20%, for example. And these are some online transaction processing workloads like that use database type of things. Okay, so I think I covered a lot of this, and I've already covered this one also. Okay, so these are the scalability curves, which are also interesting. I will not go into a whole lot of detail, but essentially you have the number of threads on the x-axis and the speed up compared to a single thread, single small core version, as you can see. And you can see that Let's take a look at some examples. Here's one example over here. In this workload, ACS, accelerating the critical section, shifts the curve to the right, meaning you get much higher performance, and the number of threads at which the performance becomes the highest changes, right? Your scalability improves. But still, you lose performance as you keep adding more threads, right? So the performance comparison points we have is probably here versus here. So the best points on each curve. That's what I meant earlier. Okay, here there are more interesting threads. So here, as you can see, we improve scalability significantly. For example, let's take a look at this OLTP workload. Baseline SCMP, symmetric multicore, and ACMP look like this, look very similar. ACMP is slightly better by accelerating sequential bottlenecks. And here, performance keeps improving, as you can see, which is nice. And as I said, the comparison point is from here to here, as opposed to here to here. Does that make sense? This is the fair versus unfair comparison. We could have easily reported a much higher result by saying, okay, everybody executes 32 threads. But that's probably is not what you want to do if you actually are trying to optimize your program, right? Okay, so I could go over this, but essentially scalability improves in 7 workloads over here. In some cases, these programs are not that improved, as you can see. Okay, so I've already said all of this, so I'm not going to go through this. Essentially, we can improve both performance and scalability by accelerating critical sections. And these are critical sections. Now we're going to generalize the idea. Because critical sections are only a part of the bottleneck, right? Can we accelerate all bottlenecks, or ideally critical paths, by executing them on a powerful core? I think in the ideal incarnation of the idea, which is not going to be the next paper is going to move the needle compared to the previous one, but it's not going to identify all possible critical paths. Because I think there are critical, ideally you would like to do this for even a single-threaded program, right? If you have a single thread, you figure out what is my critical path, and maybe accelerate it in some specialized core, maybe a large core, maybe more specialized core. It's good to think about that, basically. But we're not going to do that for single-thread programs yet. Okay, so this is the paper. You can read more about it. Let's talk about generalization, unless there are questions. Yes?
So in water, do you know how
Mm-hmm. Yeah. Yeah. This side. Yeah. Yeah, that's true. Yeah, I think it's not easy, basically. You have basically, it depends on what workloads you're targeting, but these are general purpose cores, so they're normally targeting quite general purpose workloads. Essentially, I don't have a good answer because I don't think anybody has a good answer on this one. You run a bunch of, normally the way general purpose design happens is you have a target set of workloads, which is quite diverse. You run traces, for example, you collect traces from your customers, you add your traces that are from benchmarks. For example, there could be easily thousands of traces in your trace set or workload set. And you do some design space exploration based on those traces. You run all of those traces and you try to figure out what kind of performance, what kind of energy you get. And that's very intensive to begin with, right? You need to simulate things. You cannot really run them on real hardware. So people have actually designed simulation clusters people use simulation clusters to do this sort of simulation. And then you still have limited design space exploration in the end. That's why you need to use some intuition. But here, intuition may not help easily also. So if you look at those pictures, I think Apple had 16 high-performance cores versus 8 small cores. Sometimes it's just also area constraints, right? I have enough area, so let me add more. This also is a little bit this sort of data-driven exploration is also not necessarily representative of what workloads are going to be executed, right? Because you're looking at past workloads to design an architecture for the future. And the future architecture may be executing completely different workloads, right? Parallelization patterns may be different, etc. So there's no perfect way, unfortunately. It's a combination of methodical simulation plus intuition plus some luck. Yeah, that could be said of all architectures probably, but some problems are easier, yes. Okay, so the next, unless there's another question, let's talk about how we accelerate all types of synchronization bottlenecks. And I think we really tried to cover all here. And I believe all types of synchronization bottlenecks can be expressed with the framework that I'm going to describe. And this is the paper. It's called Bottleneck Identification and Scheduling. I've already said a lot of these. Essentially, any code segment for which threads content could be described as a bottleneck in a multi-threaded scenario. In a single-threaded scenario, this is actually broader, right? Because there's no thread contention, right? Now you need to talk about critical paths, etc. Basically, any code segment that makes some thread wait, this is identified as a potential bottleneck. Serial portions clearly make everybody else wait because there's nobody else. Only one thread exists. This is on the critical path by definition. Critical sections ensure material exclusion. They're likely to be on the critical path if they're contended because they make some folks wait. But their severity may depend on how many threads they make wait for how long, right? Not all critical sections are equal because some critical sections make no one wait, right? If the critical section gets executed and no one is contending for it, sounds great. That's what speculative lock collision exploits, right? Critical section executes, no one contends, so you don't need to do any waiting. But actually, what speculative lock collision exploits is two critical sections execute the same critical section, and there's no conflict between them. One of them is modifying this part of the tree, the other one is modifying this part of the tree. And in the end, if you execute both of them concurrently, you'll get the correct result, right? But the programmer needed to be conservative because programmer didn't know that. Yes. Yes, when we talk about that, essentially you check whether you get a data conflict if someone requests the data that you updated or read. You can check that in a real processor through coherence messages. That's how they did it in that paper. Okay, we can talk more about it when we discuss coherence, etc. Okay, so that's critical section. Barriers, we've all seen barriers. Essentially, they ensure all threads reach a point before continuing. The latest thread arriving is on the critical path of the barrier. And once you fix that critical path, there could be another latest thread arriving to that. So you could actually, barriers are interesting also. And finally, pipeline stages, we've seen that also. Different stages of a loop iteration may execute on different threads. And slowest stage makes other stages wait. And that is on the critical path. So basically, we want to identify those code segments that are on the critical path in multi-threaded programs. There's also one more thing over here. These bottlenecks can change over time. So this is, let's say, cooked up example that Jose developed. Jose led this work a while ago. Essentially, whenever you come up with a cooked up example, you'll find versions of it in real code. These things exist. So come up with a cooked up example and you'll find some type of code that exists in real life. But in this cooked up example, we're going to look at copying data from a full linked list to an empty linked list. Essentially, what we will do is we're going to lock the list A, which is initially huge, populated a lot. You traverse the list and remove X from A, and then unlock it, and then do some computation on X, and then lock list B and move data or copy data from B copy data X that you've updated into B. Essentially, you insert. You do a removal operation from a shared list A and an insertion operation for a shared list B until A is empty. So you can see that this is kind of a cooked up example, but it's a nice example also. And all of the threads are going to do this. And these are different critical sections, clearly. Now, the purpose of this was to show that critical sections change, bottlenecks change over time. So this is the time of execution with some input data. I think there are maximum 32 threads over here. And this is contention, number of threads waiting for the critical section, blue one versus red one. As you can see, initially blue one is very contended, but as you keep removing things from the blue one, the contention over here reduces because the size of the thing reduces. And after some point, the red one becomes contended. So there is a part where both of them may be contended. And the red one becomes less contended after some point also because you're adding less stuff. So as you can see in this example, lock A is the limiter for some time, lock B is the limiter for some other time, and then there's some area, some time where both of them could be limiters at 2 different degrees. Okay, so that's just a cooked up example. Here's the real example from MySQL, which is actually more complicated. We're just looking at 2 locks over here and 16 threads. And we're looking at how many threads are waiting for each of the locks. And this is a fine grain, as you can see. It's millions of cycles. You can see that there are some points where the red lock is contended a lot. There are some points where the blue lock is contended. And there are some points where both of them may be contended to various degrees. Okay. So the goal is to adapt, essentially. You cannot say a critical section will be critical for good or for long. So the key insight here is actually very simple. We're going to go to the fundamentals. Fundamentals, what causes thread weighting is not good. Because thread weighting is probably loss of parallelism. If a thread weights, that's not good. It reduces parallelism and is likely to reduce performance. And the other intuition is that code causing the most thread weighting is likely on the critical path. This is not always the case, of course, but this is a heuristic that we're going to use to decide what code to prioritize to accelerate. You could use different things, of course, as we will see. So the key idea here is dynamically identify the bottlenecks that cause the most thread weighting and accelerate them. In this particular case, we're going to use powerful cores in an asymmetric multi-core processor. But you could actually do other things, as we will briefly discuss. You could, for example, increase the frequency of the core that's executing this bottleneck, right? And if we get to it, clearly there are benefits of that, right? So you don't move the code somewhere else, but then you lose the benefits on data, and shared lock, etc. Basically, you can do other things. Assuming you identify bottlenecks that cause the most thread weighting, you could do other things. Keep that in mind. So in this sense, this work is a bit more general framework. It's not saying just accelerate every critical section on some other core. It's basically saying identify the bottleneck and do something about it. Okay, so how are we going to identify the bottlenecks? That's a key question over here. So we're going to do, again, a hardware-software cooperative approach. Compiler, library, hopefully not the programmer, but if they wish so, the programmer can annotate the bottleneck code, and we will see what kind of annotations we use, and they're going to implement weighting for bottlenecks. This implementation of weighting will count, essentially associate a counter with each bottleneck, and that counter will count how many weighting cycles that this bottleneck causes for different threads. And then there will be a binary containing these BIS, bottleneck identification and scheduling instructions. And in hardware, when that binary gets executed with the annotated code and weighting implementation, the hardware will measure the thread weighting cycles for each bottleneck and dynamically figure out which bottleneck caused the highest thread weighting cycles and accelerate that. Okay, so it's a nice framework. Unfortunately, it requires changes to both hardware and software, as you can see. Let's take a look at the software changes. So this is a critical section. We try to abstract away as much as possible. So while you cannot acquire the lock, you wait for, essentially, we wait by watching an address. And then you acquire the lock once you're done waiting, and then you release the lock. Right? Now, we're going to outline this call. You don't necessarily have to, but for making things easier, you outline it using a bottleneck call. Essentially, bottleneck call, we're going to associate a bottleneck ID with each critical section. And we're going to call the bottleneck, and then the code remains the same, and then we're going to do a return, bottleneck return. Sounds nice, right? This way we can give an identification for every single bottleneck in a program. Okay, that's the bottleneck ID. Now we need to do something else. This is not enough. Bottleneck call, whenever you get to a bottleneck call, now you can say, oh, I'm going to call a bottleneck. Do I think it's critical at this point, right? So this can enable acceleration clearly. But where is the input for the do I think it's critical? And that will come from this side, basically. Bottleneck return, of course, assuming you accelerate it, now you can actually return the bottleneck, etc. So those are easy, hopefully. This is the part where we're going to change. While a thread is waiting for this bottleneck, it cannot acquire the lock. It's waiting for the ID clearly. We're going to basically increment a counter in hardware. There's a specialized instruction called bottleneck wait. While you're waiting for that address to be modified, because that's the synchronization that happens, you increment the thread waiting cycles for that particular bottleneck. So now we have changes to the instruction set to enable this. This is used to keep track of waiting cycles, and these are used to enable acceleration. Sounds good, right? And this simple mechanism can actually be used for not just critical sections, but also for barriers. This is an example where you have a barrier. A little bit more complicated, but again, if you look at the code, it's not that bad. In the paper, we have the basic code and then the change code. But essentially, you have a bottleneck call for the barrier. Here, there's a code running for the barrier. This is basically everybody executes this code, different threads. And when the barrier ends, you do a bottleneck return, right? So this is really the parallel portion of the code here. Now, once you're done with the parallel portion, you return and you enter the barrier. This is the really waiting part. And if not all the threads are in the barrier, you're really waiting. So the thread that is executing still is really exercising this bottleneck. This way you can identify the bottleneck. And the paper discusses more on how to handle barriers. I'm not going to talk more, but you can actually handle. Okay, that's barriers. This is pipeline stages, which is also, again, using this framework. You have a bottleneck call. This is really the pipeline processing. In a pipeline processing, you have an input queue and you have an output queue. You check your input queue first, get some work. If your input queue is empty, maybe you're running too fast compared to the previous pipeline stage that's supposed to be feeding you things. So you're really waiting for the previous bottleneck ID. Right. Now you do the work, assuming you get some work over there, you do the work, which is the parallel part, and you check whether the output queue is full. If the output queue is full, then you're again probably running far ahead from the thing that's waiting the results from you. Because if it was actually matching your throughput, it wouldn't have a full queue, right? So basically, the next bottleneck is your bottleneck. So you're waiting for that bottleneck now. Clearly, you could be waiting for both at different times, right? So that's the idea. This is, I think, it's a beautiful framework to really mark instructions this way. Okay, so now we've annotated this. Let's take a look at what the hardware does. With this information, the hardware can do a lot actually. As I said, identification and acceleration are independent tasks. Acceleration can be accomplished with different ways. You can increase the core frequency voltage of the code that's executing, of the core that's executing the bottleneck that's identified. You can prioritize that bottleneck in shared resources, as we have seen actually in not thread cluster, but parallel application memory scheduling. These works are actually done concurrently. So prioritization in shared resources. You can prioritize the thread in the memory scheduler that is executing a bottleneck, for example. And you can migrate to faster cores. So you could actually do a lot more, I think, but it's not limited. You can imagine things. So we're going to migrate to faster cores. Let's take a look at this. How do you measure thread waiting cycles for each bottleneck? I'm going to give you an example. You have two small cores, one large core. We're going to add a bottleneck table. We're going to modify things a little bit. This bottleneck table is going to keep track of how many thread waiting cycles each bottleneck has caused. So small core executes a bottleneck wait for a given bottleneck ID. The waiter count gets incremented, and thread waiting cycles gets counting until this small core stops waiting for that bottleneck. Okay, so you keep counting basically, as long as you have a waiter for that bottleneck. You can implement them in various ways, it's not that hard. Now, you keep counting. Now another core starts waiting for the bottleneck, same bottleneck. You increment the number of waiters, and you keep counting, incrementing the thread waiting cycles by twice every cycle. You could, of course, quantize things, etc., which the paper does, but I'm not going to go into that. Once a core stops waiting for the bottleneck, it basically notifies the bottleneck table saying, I'm not waiting for it anymore. So that decrements the waiters count. And then you go back to counting in a different way. And once the other core stops waiting for the bottleneck, this gets communicated again through the interconnect to a bottleneck table, which is located somewhere closer to the large core in our implementation. And then now the number of waiters is 0. Right? Now this way you can count the bottlenecks because you annotated the code so that you can keep track of the bottlenecks. It's nice, it's expensive. I mean, not cheap, clearly, but it's doable. Okay, now how do you decide what to accelerate? Now you assume that you have some thread waiting counts, which may be periodically reset, etc., which I'm not going to go into again. But you have multiple bottlenecks. One of them clearly has caused more thread waiting cycles than the other one. And small core gets a bottleneck call to 4600, right? the first thing it does is it queries this bottleneck table asking, should I execute it or should I send it somewhere? And the bottleneck table coordinating, it says basically, oh, that's not an important bottleneck. Go and execute it yourself, right? Don't bother me with it. So execute locally, right? And then it gets another bottleneck. This time it's 4,700. Again, it's asked the question, should I execute it myself or should I send it somewhere? And the bottleneck table says, this is important. Let me handle it in the large core. Right? That's the idea. And this way, of course, it's not that easy. Basically, it tells a small core to execute remotely. And remote execution is very similar to accelerated critical sections, basically. You need to execute. You need to send the things related to the bottleneck. Now, similar to accelerated critical sections, we have a bottleneck scheduling buffer in the large core. It gets essentially the bottleneck ID, program counter that it should start with, a stack pointer, because the communication is done, again, through the stack between the thread private data and shared data in the bottleneck, and also the core ID, so that this large core can tell when it's done, you can stop waiting, right? At some point, this gets scheduled on the large core. Right? And then large core executes the bottleneck return. Remember that bottleneck return instruction we added, which sends a signal to the core ID that initiated that bottleneck, and small core can stop waiting. Hopefully that makes sense, right? Of course, this bottleneck table becomes a bottleneck itself, at least in the communication. So what we do is we try to make the decisions locally. You don't want to go to somewhere else to decide whether you execute locally or remotely. So we add essentially cache of parts of this bottleneck table. Whenever the bottleneck table identifies that a particular bottleneck ID should be accelerated remotely, it sends a message to all of the acceleration index tables saying that this should be accelerated remotely. Meaning the default is local execution unless you find it in your acceleration index table, right? This way you don't need to communicate too much, hopefully, with the bottleneck table. And that reduces bottleneck table from becoming a bottleneck by itself. Okay, sounds good, hopefully. So basically, we've discussed both of the mechanisms, basic mechanisms, thread waiting cycles, accelerating bottlenecks. But there are also other things that you need to improve, the performance and generality of this. In the paper, we talk about that. I'm not going to talk about these in detail, but dealing with forced serialization is still a problem. There's preemptive acceleration that's important for especially barriers, but I'm not going to talk about that. Barriers need to be more preemptively accelerated. Critical sections, depending on the history, you can accelerate them later. But barriers, while the barrier is executing, your bottleneck things are, essentially bottleneck wait cycles are accumulated. And there's a thread that you need to determine that's the latest, right? So you need to preemptively get there. And there's support for multiple large cores. So in this case, we actually added support for multiple large cores so that we can accelerate things, multiple bottlenecks in parallel. Hardware cost is in the paper. I'm not going to talk about this in detail again. It's not that much. Everything is off the critical path, especially after you design the bottleneck table the way we think with caching using acceleration index tables. So the total storage cost is not a lot, but there's complexity, of course, right? Okay, again, you have trade-offs over here, which are very similar to ACS. So I will go through this relatively quickly. Now we have faster bottleneck execution versus fewer parallel threads. You have better shared data locality versus worse private data locality. We're going to solve that problem in the next work. And you have benefit of acceleration versus migration latency. Right? Okay, so we've already, I think I should actually mention this one also. Migration latency is usually hidden by waiting, meaning you migrate, but then because if something is a bottleneck, it should wait. It should not wait unless it should not wait if the bottleneck is contended, right? Basically, migration latency is not hidden if you're not going to wait on this bottleneck. But this is bad, of course, but this is likely not on the critical path. And assuming you're doing your accounting correctly, hopefully you have not migrated it, right? So that's the interesting part over here. By doing this accounting better, ACS, accelerated critical section, accelerates everything, right? Here, we basically do some accounting, and based on that accounting, we actually decide to migrate. And I think overall, migration latency is reduced significantly. So this idea is actually more general. We've talked about speculative lock collision, right? One of the issues with speculative lock collision is deciding whether you want to actually speculatively execute a critical section. In some cases, this is a very bad idea because the critical sections are going to contend with each other. And when the critical sections actually contend with each other, you run into a situation where you go back and serialize everything. So you have to recover. So if you can actually identify whether critical sections are actually going to contend with each other with this sort of mechanism, you can guide this lock elision in a much better way. So you can speculatively execute critical sections in a much better way. So this, in that sense, this mechanism is actually a framework that can enable better parallel execution. Okay, so we evaluated this again using a bunch of workloads. These are other workloads that we added to the suite. And again, we have large cores or small cores. You can read more about them. These are the comparison points. So asymmetric multi-core, we already discussed that. It accelerates serial portions, and there's accelerated critical sections. And then there is something else called feedback-directed prefetching, which is applicable to pipelining. So critical sections, accelerated critical sections was not applicable to pipelining. And feedback-directed pipelining here, actually, it's a nice idea. The idea is actually, in software, identify which pipeline stage has the lowest throughput. And if it has the lowest throughput, accelerate it in a large core. That's the idea. It's applicable only to pipeline parallel workloads, not to critical sections. Of course, a workload can have both pipeline parallelism and critical sections. In that case, these ideas are applicable together, of course. Right? Okay, but we're going to talk about that also later, hopefully. So this is the performance improvement you would get. On these workloads, ACS, accelerated critical sections, and feedback-directed prefetching buy you performance, which is good, which is actually similar to what we have seen earlier, but maybe we have more improvements in the baseline here. And if you do bottleneck identification and scheduling, you do better. And there are some workloads where you don't get a lot of performance. And then there are also workloads where ACS is dominantly applicable versus feedback-directed pipelining is dominantly applicable. So there are a bunch of workloads where limiting bottlenecks change over time that we have identified. And here, BIS actually provides a lot more improvement. And here you have barriers where ACS cannot accelerate, which is interesting. Okay, these are the results. I will not go into more detail. And it improves scalability on 4 of the benchmarks, which is not shown here. Now, there's also more analysis, which is actually a very interesting analysis, I think. It's good to do this sort of analysis. We wanted to understand why does it work? Meaning, we wanted to analyze the fraction of execution time spent on predicted important bottlenecks. And this is what this shows. This is easy to get. This part is easy to get. ACS or FDP, the fraction of execute, you can also see this as the amount of time the large core is busy doing something. You can see that if you execute only critical sections or pipeline stages, that fraction is relatively small, especially with critical sections, right? Because most of the time there is not something that the core is not in a critical section. With BIS, that fraction increases in general, not always. Meaning we keep the large core busy more, right? Okay. What fraction of that is actually critical? I mean, one of the reasons we keep the large core busy more because we ship more than critical sections to the large core, right? Not just the critical sections. We're more frugal in which critical sections we ship, but we also ship other stuff to the large core. But you can see that the large core utilization is still not 100% in many cases, or not even close to 100%. So there could be more done on the large core, as you can see. Now, what fraction of this is actually critical? This is a much harder question to answer because you need to somehow figure out, okay, you execute something. Is this really critical? Is this really on the critical path of a program? This analysis is actually very difficult. It needs to be an offline analysis. And it cannot be a perfect analysis because of the dynamic nature and dynamic changes on the critical path. But if you do some sort of analysis that is close enough, we define coverage as a fraction of program critical path that is actually identified as bottlenecks. And that increases from 39% to 59%. So it's these green bars over here. So we identify a larger fraction as bottlenecks, which is probably good because there should be some bottleneck in the program, hopefully. And accuracy is the identified bottlenecks that are on the critical path over total identified bottlenecks, which is basically total identified bottlenecks is this blue bar, and the green bar's fraction is about 72%. With bottleneck identification of scheduling, we increase coverage while keeping accuracy almost the same. Okay, that's the best we could do with the accuracy analysis. It may not be very easy to do this analysis. But basically, the takeaway is that we can identify 60% of the program critical path as bottlenecks. And about 70% of that identification is correct, which means that we're still leaving a bunch of stuff on the table, right? You can multiply 60 by 70, you get about 42%, right? Some of the things that we're shipping is identified incorrectly as the program critical path. So we're wasting resources. And some of the things we're not even identifying well. Okay, it's good to keep this in mind. So we have a bunch of more results. So as you have more small cores, you get better performance because contention increases and loss of parallel throughput reduces. I'll not go through this. If you have more large cores, it's actually good because you can accelerate independent bottlenecks without reducing parallel throughput because you normally have enough cores for parallelism. And also you can do multi-threading. Okay. So I think we have covered this. Essentially, I think I will probably say this last point over here. This is a mechanism that gives you fine-grained bottleneck acceleration with no programmer effort. Hopefully no programmer effort. If the programmer programs libraries, you could actually do all of this in libraries. You could design a library, locking library, barrier library, pipeline parallel programming library that the programmer uses, and all of these instructions are already compiled, right? That's ideally how it should be. But if the programmer tries to do a lot of tricks in the low-level code, then clearly this is not going to work. But if they're doing tricks in the low-level code, maybe they can add these tricks also to the low-level code. It's good to think about that. And this gives you a more finer-grained bottleneck acceleration with hopefully no programmer effort. Okay, I think I've covered this. This is the paper. There is an improvement over this, making better acceleration decisions. I think I'm not going to cover this. I'm going to let you study it on your own. This is utility-based acceleration. The basic idea is I'll give you the basic idea and then we're going to end early today, but I will take questions. The basic idea is to identify the utility of acceleration. Here, we made an acceleration decision based on thread waiting cycles, right? And then the next question is that good? Because we're using thread waiting cycles as a proxy for identifying a critical path. But maybe there's something else. So if you can identify each code segment, associate a metric with a code segment, saying this is the performance improvement I would get if I actually ship this code segment to the large core, that's really what you want, right? And this is what we are trying to approximate in this work. I'm not going to talk about this right now because we've talked a lot. We may start with this tomorrow, or I may leave it for you to study on your own. But we're going to continue this lecture tomorrow. Any questions? Yes. Yeah. Yeah. More large cores. Yes. Yeah. I mean, these works, that's true, but we also evaluated more large cores. So we basically always said that if you have more area, you can also put more large cores. Yes. So I think in the end, if you have area, so when we were doing this work, it's like 2008, 7, 8, because of multiple rejections of the papers. The first paper was published 2009. It was rejected 4 times, I think. But basically, 2007 and 2012 timeframe. At that point, we didn't have that many transistors. Right now, I think because there are so many transistors, people can afford to put more large cores, for sure. And also, I think examining multi-threading, because today multi-threading is relatively common in large cores, maybe not huge levels of multi-threading, but 2, maybe 4. So examining multi-threading together with large cores is useful, I think, in these. Hopefully that answers your question. Today, people do it because they can. And some workloads benefit, actually. Yeah. Any other questions? Yes. Okay, can you speak up? I cannot hear very well. Okay, we've shown examples of this in prior lectures also today, but a critical section is a part of code that enables mutual exclusion, meaning if only one thread can be executing that code and no other thread. And the main reason to have a critical section is to protect shared data, to do updates to share data accurately. Yes. Mhm. That's right. Mhm. Yes. So what we ship is, let me go back. I'm going to go very quickly. We actually ship the actual instructions that make threads wait. So maybe that was not clear, but basically you can see that bottleneck call, this is really the code running for the barrier, meaning the parallel part of the code. Does that make sense? Hopefully that clarifies it. Well, barrier instructions are really here. You enter the barrier, and this is where you actually do the synchronization. But this is really the parallel part of the code. That's right. That part, assuming this bottleneck is identified as a bottleneck, that starts getting shipped to the large core. The parallel part gets shipped. So in that sense, bottlenecks, barriers are a bit different. But also pipeline stages are also a bit different because you also ship the large part to the pipeline. Essentially, in critical sections, the critical section gets shipped. In barriers, the parallel part until the barrier gets shipped. And in pipeline stages, the code in the pipeline part gets shipped. Yeah, but barriers are a bit tricky that I didn't want to go into. There's also some preemptive acceleration that you need to do because what happens, you already entered the barrier and you want to essentially, and you get identified as a thread, right? That is bottleneck. What do you do in that case? You're running on the smaller core. So I'll let you think about that. So you need some more software modifications to indicate like which threads are running behind. Yeah, or you need higher level software constructs, meaning this is the work that's assigned to me, and this is the amount of work that I have accomplished. And that's a measure of progress. Basically, you need a measure of progress for threads. Yeah. Barriers are interesting. Okay, any other questions? I wanted to end early, and we'll end a bit earlier. Okay, I'll see you tomorrow.